All right. So I think what I'll do is just go through these. Should we go through them one at a time? There's no problem in particular I shouldn't do. And I think that, I don't know exactly the order you have things, but I've got a problem here that's dated spring 2012. In 1894, Hill developed a model of steady internal flow of an incompressible fluid. Is that the first problem? Shall we do that? Okay. So, these just go down, 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 right? They just don't stop. Okay. All right, so we're given the following. We're given a velocity field. Okay, it's in the cylindrical coordinates. So we're given a velocity field. So in cylindrical coordinates, we have, and this is axisymmetric, I should say. Okay, so do you guys know what I mean by that? Axisymmetric cylindrical coordinates, you've heard that expression before? We're going to use it a lot in this class. Axisymmetric cylindrical coordinates means it does not depend upon theta. The dependent variables in the problem, the velocity and the pressure, do not depend on theta. Okay, at most they depend on like R, Z, and T. So if it's an axisymmetric velocity field, the solution has no dependence on theta. So VR, V theta can be non-zero. There can be a flow in the theta direction, but that flow can't depend upon theta. So the velocity in theta doesn't depend on where you are in theta. It can only depend on R and Z. Similarly, the R velocity and the Z velocity cannot depend in any way on theta. So theta doesn't show up in the answer. But that doesn't mean there's not a flow in the azimuthal direction. It can be a theta. There can be a VR radial flow, and there can be an axial flow VZ. But there's no dependence in theta. So consequently, in axisymmetric cylindrical coordinates, R theta Z, okay, the solution is independent of theta. And the velocity vector V is equal to, depends only on R and Z, and I should say steady, okay, but it's steady flow. It's equal to V sub R, which depends only on R and Z, and it's in the radial direction, plus potentially V sub theta, which is a function again only of R and Z in the theta direction, plus V sub Z, which is dependent only on R and Z, and that's in the E hat Z direction. So this is the radial direction, this is what's called the azimuthal direction, this is called the axial direction. Okay. All right, and so the Hill solution this is for a spherical bubble moving in a liquid. VR, which is a function of R and Z, is equal to capital U, the speed of the bubble, over r cubed, r squared, excuse me, times rz. V theta is identical to 0, and Vz is equal to capital U over big R squared times big R squared minus Z squared minus 2 little r squared, where, what does this thing do? Where U is the speed of the bubble in the liquid, as it moves through the liquid. And R is the radius of the bubble. And you might wonder, why are we dealing with cylindrical coordinates here if this is a spherical bubble? And that's because it turns out you've got this sphere that's rising. You've seen bubbles in seltzer water, right? Rising up through a liquid. So you've got this air bubble, which is a fluid, and it's rising up inside of some column of liquid, say. This is basically telling you the solution of the convective currents of the air inside the spherical bubble as it moves up in the liquid. And the neat thing is, what this guy figured out how to do, it's really hard to come up with closed form, as it's called, closed form solutions to the governing equations of fluid motion like this. These are very rare. To be able to detail the actual local fluid motion in a two-dimensional flow, axisymmetric flow, it exactly satisfies the momentum equations. So this is a pretty rare kind of solution that this guy was able to come up with. He figured this solution out. So I don't know exactly how he did it, but I think he's a very insightful, intuitive guy. And this is what year was this? 1896, 1894. And basically, you've got this sphere that's traveling up to the liquid, and so that's like a cylindrical coordinate system. You've got radial coordinate this way. You've got the z coordinate this way, which is the direction the bubble's traveling. You've got the theta coordinate perpendicular to the cross, lying in the plane of these circular cross sections, right? So we actually solved the problem in cylindrical coordinates, even though it's a sphere, and the sphere is moving up at a very velocity u through the liquid, and you get these little currents of flow inside the sphere, of the little air inside the sphere that circulate in these little patterns. And it turns out that the components of velocity are inside the little sphere are only in the radial direction or the z direction. There's no theta motion. So as this thing rises, what you see is that it's a sphere going up. It's a radius r, and it's traveling up at a velocity u. But you get these counter currents that are flowing like this, and you get another one that's flowing like this. It's really cool solution. But you can see, if this is the z direction, and this is the r direction, and theta is like this, the flow is up in the z direction, and then it swings out radially. It's still got a z component, a radial component, but it comes down, and it's got a z component, mostly included a radial component, that comes back in. And these currents are all around this little sphere. But there's no flow in the theta direction. That's why v theta is identical to 0. And there's no dependence on theta. So this flow you see here is identical to the flow you see in this plane. It's identical to the flow you see in this plane, and this plane, and this plane, and so on. So that there's no dependence in the solution on theta. That's why you don't see theta show up in Vz or Vr. And there's no azimuthal flow. There's no theta flow. So he solved this problem without even taking account really the fact that it's a sphere. but you've got these beautiful little traces of these little encounter currents flowing within the air bubble. And the liquid outside of it is not what we're solving. We're solving for the flow of air inside, or some liquid, gas, inside the spherical bubble that we got. You don't need to have all that insight to solve this problem, but I just wanted to show you what we're looking at. I didn't bother giving you all that detail because it's not actually that important to the questions I'm asking of you, but that is the solution that he worked out. Very cleverly, he did this. So the question is, show that the conservation of mass is satisfied in a cylindrical control volume of length L and radius R. And that control volume is completely contained within the spherical bubble of radius R. Take the axis of the cylinder to lie along the z-axis and let z1 correspond to the plane z equals 0 and z2 correspond to the plane z equals L. And I want you to consider mass flux across all surfaces of that cylinder and note that a differential area element, oh, so I tell you what a differential area element is. So let's take a look at this thing. So basically what we have is, if you were to look at this sphere, okay, I'm asking you to look at a cylinder inside this sphere. I can draw, remember, we can draw a control surface inside a fluid flow problem, real or imagined, any way we care to. So I'm asking you to take a cylindrical control volume. I'm going to draw it dotted, control volumes we can do dash. So this is your control volume. And this thing is moving up like this at capital velocity u, right? And we have a control surface that has a top at z equal L and a bottom at z equal 0. Okay, and what's the radius of it? Oh, okay, so this is actually nothing here, so I should probably make this forward. Okay, so this is your cylinder that's moving up in the sphere, if you will. Okay. And so we want to show that the conservation of mass is satisfied in this control volume. Okay. So let's take part A. And we're going to look at this cylindrical control surface. Something like that. And we have R and Z. And we have n hat 1 is equal to, if this is what would n hat 1 be if we have the bottom face. What was that? Correct. And then similarly, we have an n hat. I think I call it n hat 2. And that's what? Plus e hat z. Right? And then we also have an n hat 3, which is this guy. What would you call this one? Yep. Excellent. Okay, and this is a radius R.
So is that R different than the radius of the sphere?
Yes, it is, and I think I made that, I forgot to correct that. The radius of the sphere is some big R, like R prime or something. So that must be a different R, it's a different R, so what should we call it? Well, I call that thing big R, so this would be a different R. This would be like because otherwise it's not in the sphere. So just got an assessment, cylinder control volume blank L radius R, which is completely contained within the spherical bubble of radius R. So really need a different letter. So maybe we'll call radius A. Shall we call radius A? What's that? Yeah, the inner one, let's call radius A. Okay. Gotta be a little careful with this. So this should be radius A. Because this thing is a radius R. The sphere is a radius R. So this is the center of the sphere. That's radius R. And this is a radius A. Sound good? Okay. Good. And this is Z equal L. Over here, do it on this side. This position is Z equals script L, and this position is Z equals 0. Z equals 0, Z equals script L. And now we have to remember we have a little differential area element. I gave you a hint in the problem statement. What does a differential area element look like on the surface of the cylinder? Like this. So this we're going to call dA. And that's equal to what? Let's look at a projection of the control volume looking downward. So this would be A, and so if this is X, remember Z now is coming in and out of the board. I'm looking down on the cylinder. This is X and Y coordinate system. This is theta, and this is R, right? This is a So for particles inside the control volume, it has coordinates X and Y plus some in the C plane, or it's got coordinates R and theta. But for an element on the surface, where you have a point here and a point here, and you have a differential area element inside here, and this is at Z equal L, or Z equals 0. And here you have this differential area element, and this dA is equal to R d theta dr, right? So this distance from here to here is R d theta. So this is d theta, and this distance here is dr rather, and this distance here is d theta. Okay, so R dr, this is another ds. Different ds from this one, right? ds d sigma, if you will, arc length. Dr d sigma. So we have an arc length here, but now we're in the end or on the end caps. This is along a little sliver of length of this little sliver of the cylinder wall, somewhere in the middle. This one is at the end cap of the cap. Okay. So this is just a reminder. So we have, in this case, dA on the cylinder surface is A d theta dz, but at the end cap, dA is equal to R d theta dr. Okay? So let's see how this plays out. So this is our control volume over here. And what we want to do is we want to say, okay, from conservation of mass, we have the partial with T, integral over the control volume of rho dV, plus the integral over the control surface of rho v dot n hat dA equals 0. Remember that? That's your conservation of mass. But we also know that this thing is 0. Why? How do we know it's steady? Did it say it explicitly in the problem? What if I hadn't said it? Can you see it in some other way? I do say it's a steady internal flow, so you can just say that's sufficient. But suppose I hadn't told you it was steady. In this particular problem, is there a way you could know? The answer is yes, but how? Suppose I had said steady. Exactly. The velocity components are independent of time and they depend only on R and Z. Does everybody see that? They depend only on the independent variables R and Z. So it's axisymmetric, so it doesn't depend on theta. So it only depends on the other two independent, the 3 independent variables in space, right? R, theta, and Z. It doesn't depend on theta because it's axisymmetric, so it only depends on 2 independent spatial variables, R and Z. And it doesn't depend explicitly on time, so it's clearly got to be a steady flow. But I did tell you it was steady. So you can just say, this is adequate here. And so that tells us that the control integral of the cross section of rho v dot n hat dA equals 0. But since it's incompressible, rho is constant, and cannot vanish. Or I should say, and since rho cannot equal 0, it's a constant that can't equal 0. V dot n hat dA times rho equals 0. And since rho can't vanish, the integral of the cross section of V dot n hat dA must vanish. So this is what conservation of mass reduces to for this control line. Steady and compressible flow. Now let's break it up into the fluxes. So all that's left is the mass flux term, right? The mass generation within the control line is 0. Because the generation of mass in the control is 0 because it's steady. And so that means that the mass flux across the control surface must be 0 because it's not balanced by any mass generation inside the control line. So that means that this guy we have to look at all the surfaces over which there can be flux of fluid across the control surface. So if V dot n hat dA equals 0, this is equal to the integral over the cross section of V1 over A1 rather, V1 dot n hat 1 dA. Understand wherever I drew a unit vector n hat 1, that's what I mean by the A1 surface area. It's the circle, which is perpendicular to n hat 1. Where I draw n hat 2, it's normal to this surface, which I'm calling A2. Okay, that's the circle at Z equal L. And then the third surface, where I draw n hat 3, is the surface perpendicular to E at R direction, which is the cylindrical surface of radius A. Is that clear to everyone? Three surfaces over which mass can cross. Surface 1, which is at Z equals 0, surface 2, which is at Z equal L, and surface 3, which is at R equal to A. Lowercase a. Do you agree with that? So we can break up this surface integral into the fluxes associated with those mass crossing those three surfaces. So it's this plus the same thing integrated over A2 plus the same thing integrated over surface 3. Is this clear to everyone, what we've done here? Right, this is a general statement that the total mass flux out of the control surface must be 0 because there's no volumetric, there's no time rate of change of mass inside the control line. So that means that the total flux of mass across the control surface must be 0 to balance mass. That's the case. This is the general statement of that for the compressible fluid. We break it up. those integrations break it up over these three different surfaces across which mass can flow, which means look at all the surfaces that make up that control bond, of which there are three. There's the cylindrical surface, there's the circular cap on the, at z equal L, and there's the circular cap at z equals 0. Is this totally clear to everybody? No confusion about that? Okay. All right, so we've done our bookkeeping. Oh, now we have to do our bookkeeping, right? So bookkeeping is next. So we have to have a v1.n hat 1, a v2.n hat 2, and a v3.n hat 3. So you have to look at the velocities of all these different, across all these three different surfaces. Okay. So v1 dotted with n hat 1. I think I'm going to go down. v1 dotted with n hat 1. We've already written out what n hat 1, n hat 2, and n hat 3 are. So this is equal to v1 dotted with minus e hat z, right? Because I call n hat 1 it's minus e hat z. N hat 2 equals plus e hat z, and n hat 3 equals plus e hat r. And v1 dotted with n hat 1, minus e hat z, is equal to the velocity vector at 1 is equal to minus v sub z at 1. And what is v? So basically, take the velocity vector v and take the dot product at the top, the velocity vector v, on the one surface. Is that velocity vector just three components? Take the dot product of v, right, with minus e hat z. What do you get? Which direction is it? In the z direction, right? But it's got a minus sign, right? So it's minus v sub z. So we're taking this velocity vector up there, taking the dot product with n hat 1. Okay. Actually, let's do this more generically. I want to take baby steps here. Let's get rid of the subscript 1. Just make it really simple. Okay. I'm going to take a few extra steps. So v dotted with n hat 1. Okay, is equal to v dotted with minus e hat z, which is equal to vr in the radial direction plus v theta. Well, let's get rid of v theta because we know v theta is 0. Everybody agree with that? There's no v theta, so we can just call that 0. So v dotted with n hat 1 is v dotted with minus e hat z. That velocity vector up there applies to every single mathematical point inside that sphere, and therefore inside our control bond contained within the sphere. So, what is that? Negative vz, right? Everybody see that? Right? Because e hat r dotted with e hat z is 0. You're orthogonal. Always. It's a locally orthogonal coordinate system. Where you are, any mathematical point in the field, e hat r dotted with ez is 0. E hat r dotted with e theta is 0. E theta dotted with ez is 0. But ez dotted with itself is 1. It's a unit normal. It's an orthonormal system. We have a minus sign here, so it's minus ez. Similarly, the velocity vector v dotted with n hat 2 is equal to v dotted with what? Plus e hat z, exactly. And that's equal to the same thing, vr e hat r plus vz e hat z dotted with plus e hat z, and that equals what? Yeah, plus vz. And then finally, we have the velocity vector crossing, projected in the direction of n hat 3. And that's equal to v dotted with what? Plus e hat r, exactly. And that's equal to, once again, vr e hat r plus vz e hat z dotted with plus e hat r. And what's that equal to? Plus vr, exactly. Now, we want to evaluate those three dot products at various points on the control surface, right? So we have three surfaces we're integrating over, and we've got to evaluate v dotted with n hat 1 on surface 1, right, which is at z equals 0. So we have to evaluate v dotted with n hat 2 on the other surface, surface 2, which is at z equals 0. And then finally we have to evaluate v dotted with n hat 3 on the surface little r equal little r on the cylindrical surface inside, inside the sphere. Does that make sense? So, at z equals 0, we have v1 dotted with n hat 1 equals minus vz evaluated at, for all values of r, at z equals 0. Did you see that? Now we took these dot products, but those dot products apply anywhere in our little control volume, inside our bubble for that matter. But now we want to evaluate all those points, constrain it to all those points at z equals 0 on that circular surface. So this becomes v sub minus v sub z, right, for all values of r at z equal to 0, which is equal to minus capital U going to the solution that Hill shared with us over r squared of r squared minus, let's go, what's that? No, because that's still the solution V. That's still the solution of the velocity field. That doesn't change, doesn't matter. But what it means is that the little r can't exceed little r, right? It's within that solution. So the big R shouldn't change, right? It's going to run through the solution. But let's look at VZ. VZ has a Z in it. We have to evaluate Z at 0. Does everybody agree? Because now we're constraining this dot product up here. We're constraining this guy to be lying in that plane Z equals 0. Does that make sense? So that means wherever you see Z equals 0, over here, evaluate this guy at Z equals 0. This thing is a function of R and Z. This is a function of r and z, and so is this. These are general dot products, anywhere inside our control volume. So now we have to set z equal to 0, and we get r squared minus 0 squared minus 2r squared. Great. So that tells you that we've placed ourselves at the bottom of that cylinder at z equals 0. And we've looked specifically at the dot product of the velocity vector with the outward facing normal to the bottom of that cylinder, that fell on that cylindrical surface, and evaluated the coordinates there. R is allowed to vary between 0 and A. Does that make sense? So R can vary between 0 and A because it's inside this cylindrical surface. This is a really cool problem, by the way. I just want to point out. I like this problem. It makes you think about the geometry of the problem. You've got this little sphere, the radius capital is R, and there's this fluid, this circulating fluid. Right? This fluid is just circulating. And we've basically taken a control volume, which is this little tiny control volume inside, and buried it inside the cylinder. Right? And so you have Z equal 0 here and Z equal L here. We arbitrarily chosen Z equal 0 here. Going up some distance L here. And this little cylinder is of radius little a. And we're looking at these flow patterns burst through this cylinder, right? And they burst through at the top, they burst throughout on the sides, and they burst through the bottom. They come and they just keep circulating. So we have flux across all three control surfaces. Okay. So that's good. So now we know how the velocity varies, how the velocity projected in the n hat one direction, in this case the minus e at z direction, how that velocity varies on that little disc, circular bottom of that cylinder, between 0, the center of the cylinder, all the way out to the radius of the cylinder. Now, at z equal L, we have V2, this should be vector by the way, dotted with n hat 2. Make sure you make that a vector V1. And that's equal to, from above, plus Vz. Again, but this time it's R comma Z equal what? Script L, exactly. And what's that equal to? Put an L where the Z, L squared where Z squared is, right? But it's positive as opposed to negative. So we get plus U over big R squared times big R squared minus L squared minus 2R squared. And again, this is inside that little cylinder, right? So I say this is good between R, between 0 and A again. So we've now taken care of what the velocity looks like projected in the E hat one direction on the bottom of that cylinder. That's equal 0. We've described what the velocity looks like projected in a plus E hat z direction on the top of the cylinder, z equals L. And now we have to describe the velocity field on the surface of the cylinder at R equal little a. And that's the third thing. So at little r equal little a, now we're anywhere on the surface of that cylinder of radius little a, we have V3 dotted with n hat 3, we said was equal to plus VR, evaluated at R, at what? So now when do I evaluate this at? And all Z. Not all Z, but Z from 0 to L. So now all that's left to do is an integration problem. Can I delete this thing? What's up there? I can erase this. I think this can go. All right. So now let's do the integration. So we have the integral over A1 V1, and I just want to make sure everybody remembers that when we talk about V1 up there, way at the top of the board, when I talk about V1 and V2 and V3, I'm talking about the velocity vector evaluated on surface 1, 2, or 3, depending on the subscript, and projected in the direction of the outward facing normal to that surface. That's what the dot product is doing. So the subscripts of the velocity tell you which surface we're evaluating the velocity on. To evaluate the velocity means we have to constrain the coordinates to a certain value. In this case, we're constraining the z coordinate to 0. In this case, we're constraining the z coordinate to L. In this case, we're constraining the r coordinate to A. Those subscripts 1, 2, and 3 tell us that we're constraining the velocity field on those surfaces to those coordinates that tell you that you're lying on that surface. So if you have r and z define a planar surface, r and theta define a cylindrical surface. Okay. So we're constraining ourselves to be on those surfaces, and that's what the subscripts denote. Okay, and that then tells us to set r equal to a, or set z equal to L, or set z equal to 0. But then when you take a projection in the n hat 1, 2, or 3 direction, we're saying which component of the velocity are we taking, are we pulling out? It's okay, right? It's not a 911 call.
No, I don't think so.
All right, keep working. And I'm just rewriting this over here so it's easy to see, because I've already written this equation. We've already derived to this point. And now our bookkeeping plugs right in here, okay? So now we want to integrate v1.n hat 1, where do we say that was evaluated on that surface A1, is this guy here, z equals 0. So that's just this equation. And let's pull these little coefficients out, because they're common to this whole thing, right? And by the way, they can't vanish. Big R can't be 0, otherwise this is not an interesting problem, right? And capital U is some finite value. So we can factor u over r squared out of the entire integral. So we can say there's a capital U over r squared, multiplying this entire, all three of these integrals, right? And I'm not going to fill in my limits of integration just yet. So there's a capital U over r squared. So there's a minus r squared minus 2 little r squared. Two little r squared? Yeah. Plus another integral. There's going to be two integrals here. It's a double integral, right? It's an area integral. And the next one is going to be v2 n hat dotted with n hat 2, which is this little thing. So the u over r squared is already factored out, so it's this guy. And that's big R squared minus little l squared minus 2r squared. And then finally, we've got one more double integral, and it's v3 dot n hat 3. And that's u over r squared came out az. And this whole thing is equal to 0. So you see, this is the A1 integral, this is the A2 integral, and this is the A3 integral. Okay, so let's pull this board up again, and now let's think about A1. A1 is this surface at z equals 0. We're integrating over that little circular surface in r theta. So this is the relevant area, projected area we're considering. Right? So then what are my limits of integration? And what am I integrating with respect to? For this, when you integrate over this little circular cap on the bottom of the cylinder, that's equal to. Yes, exactly. So we're integrating in r and theta, because we're integrating on the bottom cap. Similarly, when we get to the middle integral on the top cap. So we're going to integrate from 0 to 2 pi in theta. And we're going to be integrating, as you say, from 0 to little a. And this is going to be r dr d theta. Does everybody see that? We're integrating over that little cap on the bottom of the cylinder. So we're integrating in r and theta. Z is constant and fixed equal to z equals 0. So r and theta as our limits, our variables over which we integrate. It's an area integration over a circular disk on the bottom of the cylinder. So we integrate from 0 to 2 pi. Right, theta is going to swing all the way around. 0 to a, we're integrating out from 0 to a. And that's why we have an r dr d theta. R d theta is our little arc length, you know, and inside that with circular path, and then dr is the differential, is the other element of the area. And this is the same, 0 to 2 pi, because now this is at z equals 0, this is at z equals L. So this is going to integrate r from 0 to a, r dr d theta. Okay. Now what about the last one? Now we're going to integrate these little rings. These little rings that go around the cylinder, that's this projection down here, where you've got a little ds, which is now a d theta, and the height is dz. And now we're going to integrate over all z, theta swinging around 0 to 2 pi. So what does this look like? What are my limits of integration here? Well, let's do the outside one first. 0 to 2 pi, just like the other ones, right? You said it. 0 to L. And then what goes here? You got it right. I was really not expecting. I expected you guys to say r d theta dz. It's a d theta dz, remember? Because r is fixed. It's on the surface of these little rings. So it's a d theta dz. Excellent. So everybody see that? So this is going to be a d theta dz. Or you could say a squared z. Okay. So 2 pi, there's no dependence on theta in any of these integrals, so 2 pi just comes out. So this is the same thing, is saying that since 2 pi u over r squared is non-zero, this is equal to minus the integral from 0 to a of r squared minus 2r squared little r dr plus the integral from 0 to a of big R squared minus L squared minus 2R squared R dr plus the integral from 0 to L of a squared z dz equals 0. Now what I asked you to do is to show that the net mass flux out of the control volume was 0. Yes?
For the line above what you just wrote, at
Yes.
the end, should it be AZ, A, DZ, D theta? Or D theta, DZ?
Excuse me?
Should it be DZ, D theta instead of D theta, DZ?
Oh, if you like, yes. I don't think it matters really, but yes, if you want to imply that this is an integral, I'm happy to do that. Good. So, does everybody see that, right? We just integrated in theta easily. 2 pi u over r squared can't vanish, so that means this stuff in the curly braces must vanish and factor out the 2 pi. And now we just do a straightforward integration of these polynomials. Shall we quickly just do it, and then all the terms better cancel if we screwed up. Okay. So let's see. I doubt it'll work. Right? All right, so this is going to be r squared. So we have an r, that goes to r squared upon 2 minus 2. And I'm going to put this whole thing in curly braces. So we get r squared times r squared. When you integrate this, you get an r squared over 2, right? Minus, and this is a 2r cubed. So we get a 2r cubed is a 2r to the 4th upon 4, right? R cubed 2r to the 4. And then this thing is going to be 0 to a plus 2 more terms, right? This is why we don't have time limits, right? You can do this extra step. It's easy to do, right? This is a quick integration. So we have an r squared, and this becomes r squared upon 2 minus L squared times r squared upon 2. It's a very simple integration. Minus 2, this is an r cubed like that one. So we have an r to the 4th upon 4. And this is 0 to a. And then the last one is finally, a squared is a constant. So we get a squared, z squared upon 2 from 0 to L. And that whole thing should vanish. Oops, this should be close to this.
The regular show equal to the first section. It should not,
You're right, you're right. This should be in here. It should be here, right? Good. So do you believe that's 0? Huh? You can just tell by looking at it?
no, I didn't.
You did. Good job. Okay. So it should be 0, right? I said there's no way it's going to work out, but it's not. Do we want to do that? Show you? Reverse. Let's just take a minute. Okay. So here we go. So we've got curly braces here. This is minus, and the lower limits are nice. They just go away. So we just evaluate the upper limits, and we get an r squared, a squared on 2, minus a to the 4th upon 2, excuse me, plus, I don't really need these square brackets anymore, but I think I will. I'll get rid of them. I'll make this a plus. Get rid of all the square brackets. So make this a minus. Square brackets are just distracting now. And the next terms are r squared, a squared on 2, minus l squared, a squared on 2, minus a to the 4th on 2. Looks good. Plus a squared, l squared upon 2 should all equal 0. And I get rid of the curly brace. So all right, a to the 4th on 2 plus a to the 4th on 2 minus a squared l squared upon 2 plus a squared l squared upon 2 minus. This is so cool. And then these guys cancel. R squared a squared over 2. It's almost like we planned this whole thing. We have satisfied conservation of mass through no small effort. Now, I didn't show you what part B was on this problem. When I gave this exam, I don't know where we were in the year, but I suspect this was maybe the final exam. The question was on final, I don't know. But there was a part B to this question, believe it or not. And part B was just one simple addition to this. And all this bookkeeping we did pays dividends to do part B. Determine the net radial momentum flux out of the cylindrical control volume described above. Let's not do that. Right? It's not going to be in this exam. Let's go back and do this problem, in 6 weeks from now. And we'll just start off right here, and then we'll do the net radial flux out, because that'll be on these final exam. Or maybe exam 2. Not to say this problem will, but that concept of momentum flux, which I introduced for the first time yesterday, the linear momentum flux out, right? And that linear momentum flux was a term that looks like this: rho v dot n hat dA versus this is integrating over A, and this is over some control surface, and the mass flux is the one we computed. So this is mass flux. Out. And this is linear momentum flux. Out. Of control volume across the control surface. So this is the net momentum flux out. So this is the one we just did. The rho came out because rho is non-zero, so this whole thing is 0. And this one, the rho would come out because it's constant, but we're not saying this equals 0. This thing has to equal 0 by conservation of mass because there was no time rate of change. There was a steady flow. This one doesn't need to be 0. And this is, I specifically asked for the radial component of this. So the net radial linear momentum flux out would be V sub r right there. Okay? So net radial linear momentum flux out would be this. Would be the integral of rho over the control surface of V sub r times V dot n hat dA. So what I asked you to solve in part B of that problem, which we didn't share with you, was to evaluate this integral, where we take the radial component of dr just give it to you. And so instead of computing this integral, it's this whole thing multiplied by the radial component without it on the surface. That's not going to be necessarily 0 at this point. So, we're not going to do that now, but it's just basically taking this very same thing and then multiplying each of these terms, those dot products, multiplying by the radial component evaluated on those respective three surfaces, and then integrating them. Okay, so there's that. What's next? Any questions about that? Yeah. Typically, I have 2 or 3 problems. You just say, Raj?
3.
3. But you know, I am going very slowly here. I'm taking these baby steps because I really want. This is the time to take time to go through the problems very carefully and systematically. I do expect you to show us this detail, but you're not going to be explaining it to anyone. So it won't, you know, it took us a while to write this down and go through it and make sure you guys understand we're evaluating on this surface, on that surface. Do a few of these problems, work through these problems. So go home, once we work through them tonight, go home and look at a blank page again. Those problems that Raj emailed to you, these very problems, go do them again. But don't look at the notes. Just say, what can I capture from what I just saw in this review session? Go through those problems again and see where you get. See if it makes sense. And once you get stuck, you can go back to this and hopefully it'll all come together. So you'll have you'll practice the mechanics of it, so that when you see the exam, you'll be able to move through these things faster. So it's going to take. So you have a whole week to do that kind of preparation. We wanted to get this review session in before the weekend. So after this review session, we're going to post the solutions that I'm going through here, which are in your notes, but I'm going to post the detailed solutions. Raj will on Blackboard tonight, so you have them through the weekend and all next week to prepare. But go through this and do these exercises again on a blank page. Yeah.
Because we know that's not going to come from double integral because we end up as canceling.
Yeah, but I want you to show me that you know it's a double integral. You're integrating over an area, but 2 pi shows up on all the terms. So I think it's important to show that step so we know you understand that this is an area integration. And it's just that in this case, it doesn't generate anything but a constant that is common to all.
Those are correlated because there's no dependence.
That's right. It is because it's axisymmetric that the same 2 pi constant shows up when it work to do part B. So it's a 2-part problem where most of the effort was in part A. Okay. We may have a 3-part problem or 2 3-part problems, which are, and that's it. Or maybe we have 3 2-part problems or something like that. So there usually are part A, B, and C, or part A, B in these problems, and we'll have 2 or 3 problems depending on how many subsets there are. Just to give you a sense of the logistics of it. Okay. And they're not all equally weighted, right? So I might have a problem. If I have 3 problems, I might have one worth 20 and 2 worth 40. You know, or I might have a 30, 30, and a 40. So it just depends on what the level of involvement is in any given problem. I'll just distribute the points. And when we grade, though, we're very consistent. So if Raj will grade all of problem 1, and Sam will grade all of problem 2. So this consistency, it's not like Raj will grade half papers, and Sam will grade half papers, and they have this difference in the way, you know, they grade it. You have the same person grading all 1 problem. And so that makes it all uniform. Points are distributed for the evaluation of sort of objective evaluation of how that 1 problem is. So the next problem I have here is from spring 2010, an incompressible fluid with constant density rho flows vertically against gravity in a duct of non-uniform circular cross-section. Is that the next problem we should go through? All right, let's do that. I think this is a really good problem, as I mentioned, because, if I do say so myself, because it does ask you to think about the geometry of the problem very carefully that you're working on, but really challenges your understanding of where the fluxes are going. You have this curved cylindrical surface, you've got fluxes of mass across it. You've got end caps top and bottom, there's flux of mass across the top and the bottom, and the integrations over those surfaces with the velocities being evaluated and constrained to be on those surfaces is what you're really showing us. You understand what you do. Okay, that's why I like it. And it's pretty cool that, the whole thing, we just grabbed a cylindrical chunk in the middle of this flow field that's an exact solution to the governing equations. And indeed, mass is conserved. For any little cylinder we could draw in there that's centered along Z0. And in fact, it's true for any cylinder, any kind of shape you can take at all, because mass is going to be conserved. All right. Okay, next problem. Incompressible fluid with constant density. I guess I should write the problem down, right? Spring 2010. Forgot to do that in the other one. Okay. So an incompressible fluid with constant density rho flows vertically against gravity in a ducted uniform circular cross-sectional area A of Z. Is equal to pi d squared, which varies with Z, upon 4. With constant volumetric flow rate Q. All right, so what to say? An incompressible fluid with constant density flows vertically against gravity. So gravity is definitely going to be in this problem. And it's an incompressible fluid. Say incompressible in parentheses. Okay, so that's what we're told. And part A is if viscous effects are negligible, derive an expression for the local duct diameter. So, if viscous effects are negligible, derive an expression for the local duct diameter. So, get some weird duct, right, that varies with Z. So, it's a variable cross-section. This fluid is flowing against gravity, vertically, I guess you could say, if you choose gravity to be out there. We want to solve for D of Z, assuming that viscous effects are negligible. And D of Z can be written in terms of D naught, the inlet duct diameter, is equal to 0. That would be necessary to maintain constant pressure throughout the duct. So basically solve and neglect effective viscosity and find D of Z if the pressure is constant throughout. Okay. So, we're going to assume steady flow. Inviscid flow. We're Select effects of viscosity. And I think we said that the inlet at z equals 0, d at z equals 0 equals d naught was given. Okay, it's the dark inlet, so flows coming in at z equals 0. Okay, so what do these things call out when you look at these simplifying assumptions? It says Bernoulli, right? It screams out Bernoulli equation because you've got a steady flow, it's incompressible, and it's inviscid, so there are no effects of viscosity. So this is the kind of thing where we can certainly integrate along the streamline and expect that the sum of the static pressure, the dynamic pressure, and the gravity force are all constant. So, from the Bernoulli, the Bernoulli equation applies in this case. Along a streamline. And we have P at the inlet, right? P naught plus 1/2 V naught dotted with V naught plus rho G Z naught equals P at 1, some other place along the flow, plus 1/2 rho, oops, there should be a rho here. V1 dotted with V1 plus rho G Z1. Now we know that P1, if P is constant everywhere, what can we say? If P's constant. Yeah, so P naught equals P1. Okay? And taking, as we have, Z naught equal to 0. And Z1 equal to some arbitrary Z. You know, just say anywhere in Z. We get 1/2 rho V naught squared is equal to 1/2, oh, I guess I should say Z equals Z and V1 equal to V of Z. Okay. Then we get 1/2 rho V of Z squared plus rho G Z1, but we're just going to call that Z, generally speaking. So that's what the Bernoulli equation reduces to, for some arbitrary position along that streamline Z. We call it Z1, we're just going to call it Z generally. Assuming that Z equals 0 is the point of the streamline that we're starting with, and we're going to integrate to some other point Z downstream, or up, further up on Z. But we need to also use conservation of mass. So from conservation of mass, what do we know? Partial with T, integral over the control volume of rho dV plus the integral over the control surface of rho v dot n hat dA equals 0. And we know this is 0y, the steady flow. And since rho is constant, comes out of the integral. Right, and it's not vanishing. Rho equal constant implies that we can pull the rho out. And then since rho cannot equal to 0, cannot vanish, it implies that the integral of v dot n hat dA must vanish. Okay. Oh, CS. Okay. So, now let's go over this board over here, so I can keep all this going. So now what we have is that the integral over the control surface of v dot n hat dA vanishes, but that is broken up into the integral over the control surface A1, or an A naught, I think we call it, of V naught dot N naught dA, plus the integral over the control surface A of Z, somewhere downstream, because A varies with Z, of V of Z, dotted with N hat dA equals 0. So if you will, some weird control volume like this. Fluid is coming in. This is Z equals 0. And then somewhere along the line here, this is Z. We've got some velocity V naught. Here we've got some velocity VZ. Right. We have an outward facing normal N hat naught. We have an outward facing normal N hat. Okay. You also have, these weird outward-facing normals here, and at 3, if you will, but there's no flow across the duct. Okay, so there's no velocity flowing across 3. Okay. So then this becomes, do the bookkeeping again. Oh, I have bookkeeping right here. It goes to me. And what do we have here? We have V naught equals V naught E hat Z. Oh, is this my, it's Ed Raskin. What's that? I'm sorry to do that to you guys. I think it's like 6:30 now.
What's that?
When do we expect these guys to call?
They said they'll try to do 6:30, but it could be somewhere between 6:30 and 7.
And are they calling me?
Calling me.
They're calling you?
Yeah.
Okay, even better.
Yeah.
Okay. So that was Nebraska. You can send them a text saying we're doing a 6-hour review session.
Sure.
Join us if he wants. Skype him in. Okay. So V naught is equal to V naught in the E hat Z direction, and N hat naught equals minus E hat Z. Right? This thing is equal to minus E hat Z. And this guy is equal to plus E hat Z. So this dot product, V naught dotted with N hat naught, is equal to minus V naught, and V of Z is equal to scalar V of Z in the plus E hat Z direction, and N hat is equal to plus E hat Z, such that V dotted with N hat is equal to plus V of Z. So here's our bookkeeping. And that leaves us with the integral over A naught of minus V naught, is this whole thing here, is equal to minus V naught. And this whole thing here is equal to plus V of Z. Good. So we got integral of minus V naught dA plus the integral over A of Z V of Z dA equals 0. So minus V naught times the integral over A naught of dA plus V varies only with Z, right? We said it's uniform over E cross section. Varies only with Z, so it comes out of the area integration, because the area is the area from the cross section here. It's this area projected in this direction. So this is the integral over AZ. So what is this area integration? What is this integrated to be? A naught, right? So this is minus V naught, A naught, plus V of Z. And what does this integrate to be? And what is A naught? These are circular cross sections. Yeah, what's A naught? Yeah, D naught squared. So we get minus V naught by D naught squared upon 4 plus V of Z times what's A of Z? Not D squared 0, right? Because this thing has, yeah, this, yeah. So this is pi times D of Z squared upon 4 equals 0. Okay. So this tells us that V of Z is equal to V naught times D naught upon D of Z squared. Okay. Now, let's get rid of this board down here. We want to get that volumetric flow rate. And that makes sense, right? So this is what we've seen many, many times over. I'd just like to make sure you guys can derive this systematically from conservation of mass. So it's good to go through these steps and write this stuff out. So we also want the volumetric flow rate. Q is equal to the integral over any area. Oops. So it's the integral over A naught of V naught dA, and it's equal to the integral over A of Z of V dA. So this is just equal to V naught A naught, which is equal to V of Z A of Z, right? So Q is equal to V naught times pi V naught squared over 4, and it's also equal to V of Z pi D of Z squared upon 4. So that's the volumetric flow rate. Now we have to go back up to this guy. So this is the other result we got from our force balance Bernoulli equation. So from the Bernoulli equation, we need to combine these results. We have GZ, so there's a rho that shows up in every one of these terms, right? It's a constant density, so this cancels out, right? So we have GZ is equal to 1/2 V naught squared minus V of Z squared. Everybody agree with that? Or twice GZ. And we can, if you will, we can write this is therefore we can factor out. So this is equal to 1/2 V naught squared minus, see VZ up here? That's a V naught. So if you square this whole thing, you get V of Z squared is equal to V naught squared plus this thing to the 4th power. Right? So it's V naught squared minus V naught squared D naught upon D of Z to the 4th power. And the V naught squared can be factored out. So we get V naught squared upon 2, 1 minus D naught over DC squared, over D of Z rather, to the 4th power. So that's G times Z. And I think the question was to solve it in terms of D of Z. So this effectively is the answer. We'll just rewrite this in terms of D of Z. So, and Q, I think it said write it in terms of Q. And we have a relationship for Q. So we have a V0 squared here. So if you will, V0 is equal to Q, or the 4Q, right? 4Q upon pi D naught squared. So we can now, where you see this, we have G of Z, G times Z, is equal to 16, there's 16 here, I guess it'll be 4Q upon pi D naught squared, all squared. And it's over 2, so it's 1/2 that, times 1 minus D naught over D0 to the 4th. And then you can rewrite this, rearrange this if you want, so that you get D of Z is equal to D naught times 1 minus 2G Z times pi But as far as I'm concerned, you largely solved the problem here, because you've got an equation that depends only on D naught, Q, G, and Z. So you have a relationship between D of Z and D naught. So this is a statement. Let's see if that was right. Yeah, that was good. That's not quite right. This is GZ. Let's see if that was right. This is D naught, right, times 1 minus GZ. That's pi squared D naught to the 4th all over AQ squared. That was right. There should have been a factor of 2 there. But this is just a little bit of algebra. So D of Z is equal to D naught, 1 minus G times Z times pi squared, D naught to the 4th over AQ squared. So here you see how D of Z varies with D in this funny channel, right? So that it satisfies the Bernoulli equation and conservation of mass for an incompressible, steady, inviscid flow. Okay. What's that?
Why is, so D of Z is the diameter of the channel, right?
At any arbitrary point Z downstream of Z naught.
Why is it dependent on gravity?
Because the Bernoulli equation is what's driving it, right? It's
Right,
flowing
right.
up against gravity,
Okay.
right? So basically, as it moves up, it's got kinetic energy, right?
Right.
And so its kinetic energy is changing because the channel's changing in diameter. And as the channel changes in diameter, right? The channel changes in diameter, the speed of the fluid particles changes because where you have wide cross-sectional areas, you have slow flow. Where you have narrow cross-sectional areas, you're throttling until you have high velocity. So the kinetic energy is changing as you move up in Z along the streamline. But you're also increasing your potential energy as you move up against the force of gravity. So it has to be dependent upon how much you're increasing your potential energy. So if you did this experiment on the moon, it would be a different, the relationship would be the same. But this term would be weighted more heavily on the moon than on the Earth, because your potential energy isn't growing as fast as you move up off the surface of the moon as you move up off the surface of the Earth. So it's got to depend upon that potential energy term, which is inherently dependent upon the acceleration of gravity. Good. Now this satisfies Bernoulli equation, right, which is like the conservation of momentum, if you will, for an incompressible, steady, and inviscid flow. And it satisfies conservation of mass. So as you move through, as you move along that channel, you're always conserving mass. The VA is, V times A is always constant, or the volumetric flow rate is constant. So that means that the flow rate over this cross-section, this cross-section, this cross-section, this cross-section is always constant. So it's quite an easy matter to plot this thing. Let's see what it looks like. Let's see how that shape looks. Okay. Yes?
So if in the problem statement saying that the fluid is incompressible, do we have to do that entire derivation of conservation of mass, or can we just use the flow is equal to velocity times the surface times the area?
I wanted to see this. It's not that much work, right? It's just 2 lines. You start with this, and then you systematically show me that you know how to do this. It's really just 2 steps, and then you're at this point. I guess it's 3, because once you get to that, then you have to break it up. I want to see the bookkeeping. I want you to show me that Q equal VA, right, for uniform velocity. But it's not always going to be that case, because I could have a velocity that varies over the cross-section, in which case you definitely have to carry that relation.
Okay, so I guess it's similar, but did you need 3 equations?
I only use 2.
Right, but you did
Conservation of mass and
conservation of mass and
Bernoulli.
flow rate and.
Well, that's not really a different equation, right? I'm just being mindful of the fact that, I don't know where I put it, over here. I asked you to solve the problem in terms of Q. So to do that, you've come up with this relationship between V naught and V of Z, right? That comes from conservation of mass. And then, I guess you could say it's another equation, but it's really just a definition of the volumetric flow rate. Okay? So here we're just saying that Q is equal to this, and because Q is constant, these things have to be equal. But that comes from conservation of mass, right? So the fact that these things are equal is really a statement of conservation of mass, which you've already written. Right? So this is a statement of conservation of mass because we've already put in, we've taken, it's this equation here. So that means this equals that. So I can bring this to the other side of the equation, the minus becomes a plus, which is what this is. So I'm rewriting conservation of mass and noting that that is equal to Q. Instead of each of these terms being zero, they're not. They're equal to one another. So sum those two terms that is zero. Minus 1 plus the other. So I wouldn't regard it as a different equation. I would say this is a consequence of conservation of mass, which you've already established up there. And that's equal to Q, because that's the definition of Q, is terms. And then we realize that these things are equal. VC is related to V naught this way. And so, which really comes from all this, right? This is really conservation of mass allows us to do this. This statement here, bringing this over to the side, we can recognize that as Q. I didn't want to just say that bring this over to the side and say, oh, by the way, that's Q. I want to remind you, Q is that's the definition of Q. It's V integrated over the cross-section area. In this case, V comes out of the interval because it's constant in the cross-section. But it doesn't have to. Other questions? There was another problem associated with this. Probably, again, this might have been a final exam question. But the next question, if you're interested, was if SCS effects are not negligible, then derive the expression for the head loss, which you guys haven't talked about. That's income from conservation of energy. So there'll be a second part to this where you'd actually apply conservation of energy instead of the mill equation, which accounts for viscous losses. All right. So the next problem is one of an ideal vortex. Oh yeah, another question.
Do you
Yeah.
have to put it in terms of Q, because it just says VC in terms of do not, could you leave it in terms of velocities, or you could just.
Absolutely, you could, but I thought it did say it. Did it mention Q?
If we have a Q and you tell us it's constant for the Q, is that implied that we?
Oh, with a constant volumetric flow rate Q, so I wanted you to use that variable, but it's
Oh, okay.
I bet that question was asked during the exam. And I said, yeah, please write in terms of Q instead of V naught. But there's nothing wrong with writing in terms of V naught. Yeah. I probably should have said, see, in terms of the diameter D naught, and I should have said Q,
Yeah.
and the duct inlet Z naught. I should have said Q. Those are mistakes. I'm sure I got a question during the exam about that. Why is Q showing up here? Okay, the next problem I have is, how many problems were there altogether that Raj had? Do you know? 9 or 10? So we're doing problem number 3 now? All right, let's keep working. We got a lot of work to do, guys. But we can't lock my car in the garage. Okay. So at like 10:55, we should hustle to the garage, or maybe 10:45 instead of running. We could walk there. Sound good? Yeah, I get some time. But we gotta eat pizza, so we got a lot of work to do. All right, so let's do the ideal vortex problem. And the ideal vortex problem is not too dissimilar from the one we did with the Hill vortex. So this actually will be a simple, we'll be able to get through this faster. Because I won't have to go take such baby steps. It's a good exercise to do this one. Again, sort of as practice. But I think we'll be able to move through it faster. Very much like the other one. Okay. Ideal vortex of an incompressible, inviscid flow of a circular, has circular streamlines, where the fluid velocity is given by this thing. And gamma is some constant, it's known as the circulation. All right, so we've got, this is this Asine vortex. Okay, so basically what I'm showing you is that there is this thing called an ideal vortex, V theta R. Is equal to gamma, which is some constant, upon 2 pi over R. So this is what's called an ideal vortex, right? So you can talk about something where you have velocity in the theta direction. So think of like a tornado, it's a vortex, right? So imagine a tornado. right, where you have some constant circulation. How fast this fluid circulates is captured by this constant gamma, right? So the strength of the vortex or the strength of the tornado is captured by gamma. You double it, it's twice as strong, or the tornado destroys twice as many houses, if you will, twice as big a house, right? But it drops off like 1 upon r. Well, that's not physical, right? Imagine, if you will, v theta is the velocity in the theta direction. As r goes to 0, what happens to v theta? One of 3 answers. It goes to infinity, right? It's bad news, right? We don't have infinite velocities. We never exceed the speed of light, let alone infinity, right? So that becomes a singular solution. We do not have infinite velocities at the center of tornadoes. They may be high velocities, but they're not infinite, right? They're bounded, they're finite. We have viscosity becoming important as you go toward the core of a tornado, okay? And that bounds the problem. We don't have an infinite flow. So basically, this characterizes the gamma characteristic of the vortex. At the origin r equals 0, the velocity becomes unbounded and the solution is unphysical. Right? In reality, viscous forces arise in the core of the vortex that bound the velocity at the origin. So this fluid velocity above does not satisfy this condition as an unbounded solution. In order to remedy this situation, an unsteady velocity field was found by this other guy, Asin, who's probably good friends with Hill. I don't know how these guys figured these things out, but they were very clever. And Asin came up with the so-called Asin vortex, which also satisfies the governing linear momentum equation, like Hill's vortex, Hill's rising bubble problem does. And I don't know when he did this, though. I'd like to know what year that was. And basically, so it was found by Asin, the so-called Asin vortex, which solved the decay of this ideal vortex above that which that would arise due to viscous forces when at time t equals 0, a stagnation point in the flow was suddenly and permanently imposed at the origin. So basically, this thing depends upon, this is a time-dependent solution, it's Asin vortex. So what they have is, what Asin came up with started with this idea, but he fixed it. And he added this other term and made the whole thing a function of time. So this vortex depends upon time. This is an unsteady problem. So this is gamma upon 2 pi r. So it looks like it's got that same ideal vortex as its first term, but then it's decaying exponential. So it's minus e to the minus r squared upon 4 nu t. Now, at time equal to 0, what's v theta? What's that? So basically what we see here is, so let's read what it says. So in order to remedy the situation, an unsteady velocity field was found by Asin, which solved for the decay of the ideal vortex above that would arise above that would arise due to the viscous forces when at time equals 0 a stagnation point in the flow is suddenly and permanently imposed at the origin. So basically, let's take this this vortex, right? And at any time t, positive value t, you've got oh, I guess I shouldn't get secret. Okay. Well, basically, what's happening is, if you were to, at time t, a stagnation point in the flow was suddenly and permanently imposed at the origin. So if you have a stagnation point in the flow, what does that mean? What's a stagnation point? The velocity vector vanishes. So here we're saying that if a stagnation point in the flow were suddenly and permanently imposed at the origin, okay, so that we don't have this unbounded situation, but we have a scenario where we have a stagnation point, right? So we have a scenario where the velocity is 0 and bounded at the center, okay? And then that's gonna, through the action of viscosity, that 0 velocity is gonna diffuse out through the vortex and kill the vortex over time. Okay, so we're gonna rob it of its energy. So over time, viscous forces would progressively destroy the vortex. So this decaying exponential as time gets bigger and bigger and bigger, right? This thing decays away to 0. And so t gets very, very big, and this whole thing, I'm sorry, what happens as time gets bigger and bigger and bigger, t gets bigger and bigger and bigger, right? So this exponential, right, this term goes to 0, e to the 0 as time gets very, very big is 1. 1 minus 1 is 0, right? So that goes to 0 faster than 1 over r does, and this thing, as time goes to infinity, this thing decays to 1, approaches 1 minus 1, which is 0. So the exponential growth in t grows faster than the algebraic growth in r, so we get a bounded solution everywhere. And as you suddenly a timing to 0 impose this, this stagnation point at the center, viscosity robs the rest of the vortex over time of all of its momentum. And this term grows and shrinks the velocity v to theta over time. So the fluid velocity field that is associated with the Gaussian vortex is given by this thing. And the constant nu, by the way, is known as the kinematic viscosity. We haven't introduced that. I think I talked a little bit about dynamic and kinematic viscosity at the beginning of this lesson, but that's really not important to this problem. I just want to let you know that it's a constant, just like kinetic is. Okay, these are just parameters. One characterizes the strength of the vortex, and one characterizes the strength of the viscosity of the fluid. A very viscous fluid would see this vortex decay faster than a much less viscous fluid over time. Okay, so show that by the conservation of mass is satisfied in a fixed cylindrical volume that is of height h and radius r, and take the axis of the cylinder to y along the z-axis. And that's the only thing we're going to work on today. So let's do this one. So this is spring 2012. Number 3. And this was an exam problem Raj took, right?
Yeah, I
Had to be. He took this class in 2012, spring of 2012, so he had to do this problem. And he looks good. He was much taller back then, but he looks great still, I think. So he made it through no problem. And look, now he's teaching the class. All right, so we have v theta over 2 pi r times 1 minus e to the minus r squared over 4 nu t. This is not a steady flow. Clearly, depends upon time. Nu and gamma are constant. Okay. So, we need to show that the conservation of mass is satisfied. Cylindrical control volume. Okay, so let's draw it. This is our cylindrical control volume. Okay, and it's of height h. We're told. And it's of radius r. And we've got some little radius r here. And we're going to have, in the usual way, we're going to have an outward-facing normal, n hat 2 at top. This is the z-axis. This is r, and this is z. Okay. R can swing anywhere around. And this will be an n hat So this is Z. This is an n hat 1. This is the velocity field. It varies with r, and it varies with time, and it only has a theta component. So VR and VZ are 0. Okay, so VR and VZ are identically 0. This thing is a vortex. So there's only flow in the theta direction. Okay, unlike the Hill bubble, where there was only flow in the R and Z direction, there was no flow in the theta direction. Okay, so we have an n hat 3, which is this one. Okay. What do you think V3 is going to be? Yeah, right, there's only flow in the theta direction. There's no flow in the radial direction. So there's no way flow can cross the plane. Right, so we know V3 is identically 0. Gotta be, there can't be, it's only a theta flow. Theta is orthogonal to n hat 3 direction, which is equal to E hat R. And then the male of right one thing here, make it clear. N hat 3 equals E hat R, and therefore, and we know V3 is 0 there. Well, should I say that? I shouldn't say that. I should say, I don't want to say that. I think what I want to say is, yeah, let's just leave it at that. We know that there's no flow in the radial direction, so that V3 dotted with n hat 3 is 0. There's no flow in the direction, so there's no projection. So VR is 0. Wow, pizza 0 already?
Pizza is here.
How did you handle the tip?
15%.
Oh, thank you. Great. So, and that was on the, they put that on my card, didn't they?
Yeah.
Okay, so let's just finish this real quickly and then we'll pull out the pizza, okay? Because we do want to get 3 problems done before we stop. So, those are our 3 outward facing normals, and as usual, we're going to say from conservation of mass, the integral over the time of value of the integral of over the control volume of rho dV plus the integral over the control surface of rho d dot n hat dA equals 0. Now this term is 0. Why? Steady, right? Steady depends explicitly on time. This term's not 0. I was just seeing who's thinking about pizza and who's thinking about getting this problem. Okay, that's not 0. This term, we gotta keep this sucker. Don't like it, we gotta keep it. No reason to throw either of these terms away, all right? So now let's do our bookkeeping again. But it's bookkeeping we're quite familiar with, right? We've seen it before. So, I'll write it over here. Okay, so V1, let's just recall that the velocity vector V is a function of R and T, and it equals V theta, which is a function of R and T, E hat theta, right? So recall that VR equals VZ identically 0. Okay. It's very simple velocity profile. It's just some function of 1 over r times 1 minus this decaying exponential of time. And by the way, we also don't have a singularity either, because if you were to look at as r goes to 0, you have for all time, that second exponential term will control the growth in that. So you'll have to apply L'Hopital's rule to show that, but you can show that this thing is well bounded. Okay. So, well, this is bounded, the growth is controlled. So V1 dotted with n hat 1 is equal to, well, what is V1? V1 is the velocity vector evaluated on the surface that's perpendicular to n hat 1, which is that circular end cap to the cylinder, right? So that's just V at, for all R and T at Z equal H, although it doesn't really matter because this is independent of Z. So it's V at R and T dotted with, what's n hat 1? Huh? E hat Z. So this is just equal to VZ. I'm sorry, this is just equal to V theta of R and T. E hat theta dotted with E hat Z. And what's that equal to? That's 0, right? That's 0. So there is no VZ in this whole problem. And so if you extract the Z component of the velocity, you get 0. And then you have V2, similarly, equals V of R and T, dotted with minus E hat Z. Similarly, what's that equal to? That's 0. And then finally, we have V3, dotted with N hat 3. And that's equal to V R equal to what? Big R, because we're evaluating on the surface, dotted with, what's n hat 3? ER. Right, and so that's equal to what? Also 0. This is very interesting. This term, second term, is gone. There's no mass flux across the surface. Okay. Good. So, then that says that this implies that the integral over the control surface of rho v dot n hat dA equals 0. Identical. Well, it's equal. That's 0. It's not identical, it's just 0. All this is 0. So that means that all that's left is the partial with t integral over the control volume of rho dV equals rho partial with t integral over the control volume That's a really boring problem. I know why I'm doing it wrong. Times dV equals rho times dV dt. And this is really dumb. It's rho times dV dt is the time rate of change of the volume, which is pi r squared times h. And that's equal to 0. It's really dumb problem. But it's because it's much more problem to this than this problem. So this is rather simple to show you that all the flux over the control surface vanishes, which means there can't be an accumulation of mass in the inside, right? Or net loss of mass across the control surface. So it better be that the volume integral vanishes too. Time rate of change of a constant volume, which is our control volume, can't change. We don't have a change in control volume. It's fixed control volume, so the time rate of change of it is 0. Density is constant. And there's this is the exercise here is totally a bookkeeping exercise to show you that all contributions to the total flux, mass flux, are each term by term 0, so the sum of the three is 0. Now the reason this problem is interesting is because of part B, C, and D, which we're not going to do because it's beyond the scope of what we talked about. Part B has to do with the rate of momentum flux across the control volume, or in the control volume across the surface. And what is the net momentum flux out? So it's again using this bookkeeping, but you're not going to get zeros anymore. When you start doing the bookkeeping, you're going to have you're going to have some non-zero momentum flux terms. And certainly, actually that's not even true. What you're going to have is you're going to have this generation term. Where is it? You're going to have the partial with time integral of control volume of rho v dV That's not zero, right? That's definitely not zero. But that's balanced by some viscous force, which we haven't talked about. We're going to start talking about that next week. But that's not on this example. So part B and C had to do with the momentum flux, which is zero, but you're going to start to see that there's net instantaneous change in momentum in the control volume, and that's balanced by viscous losses. Okay. And then finally, assuming that the pressure is constant throughout the field, what quantity balances the total rate of change of momentum? It's got to be viscous forces. If there's no pressure, if the whole thing is equilibrated with pressure, with that atmosphere, because the thing's a free vortex in atmosphere, everything's in atmospheric pressure, then we've got this circulating vortex, and the momentum of that is decaying away, and as we lose momentum, it's being lost to net viscous forces that are draining it. And we're basically, the friction that's associated with the viscosity of this slowing down this vortex is starving it of its energy, and therefore draining off its momentum to ultimately zero. So that was actually a pretty quick problem, because the other subparts were really from material we're going to cover in the second half of the semester. So we didn't have much to do there. So let's take a break. And I think we will do the rest of that problem in 6 weeks from now, right? I think it'll be a good problem to do. Do you have a question? No. No more questions about that? All right, so we'll start our fourth problem after we take a break. We're going to set this up. All right, this problem, we're going to do all three parts. This is spring 2009. Number one. Okay, so a Bluff half body, so what do we mean by that? I use that term, and a lot of students raise their hand in class saying, what is a Bluff body? And nobody seems to know except fluid mechanics, so I imagine they made it up. So basically, think of this as like a blunt surface that disturbs a flow. So a car could be a Bluff body put into a flow, right? Into a wind tunnel, right? You could take a aircraft fuselage and stick it in there. A sphere in a flow is a Bluff body, okay? So it's some disturbance to the flow that's imposed by the presence of some solid bounding volume. So there's this curious shape. It's called this particular Bluff body is neither a sphere nor a cylinder. It's some odd shape. Gives rise to a particular velocity profile that I'm going to share with you. So a Bluff half body is stationary in a steady cross flow of an inviscid incompressible fluid having density rho. So you've got inviscid, incompressible, and it's steady flow. So that should ring all kinds of bells, right? What does that make you think about? Bernoulli equation, exactly. So when
So we already did one Bernoulli. Do you want us to state assumptions when we're doing our problems out? So like we have to state 2D as well. Then you like go in with there's 4 assumptions.
Yes. So it certainly wouldn't hurt if it's a 2D flow. Like in the case of this problem, it's r and theta.
So even though it's
so this is clearly a two-dimensional flow, right? But
so like will there be points awarded to saying like assumptions, inviscid, steady?
as long as you know what those mean, and so then you're going to have to show that you know what does it mean to be incompressible, and then yes, we typically give you some credit for that. But just stating it, it's kind of in the problem. So you need to tell me what does that translate into, and then we do actually credit you for those kinds of things.
How do you show 2D flow in that case?
So that one, you're going to state it, and you see that it's just got 2 components. So one way to show it would be to have 2 momentum equation components instead of all 3. Right? So if it's a conservation of momentum, it might not be relevant to say it, but if you're looking at the conservation of momentum, you're only going to take a dot product with 2 of the base vectors. It's a 2D flow, so you had x and y, say. You wouldn't need to do the 3rd component. Okay? That's the way you would show it in a problem where it's relevant. Where it's not relevant, you can state it, but it doesn't matter. But there may be instances where it does. Like flow in the plane, in the xy plane, that's a 2D flow, and you'd say there's no z component. And you'd show only 2 components of the momentum equation. All right, so this is a steady cross flow of an inviscid incompressible fluid, so we can be pretty sure we're going to be dealing with the Bernoulli equation, okay? At some point through this problem. The velocity field in the r theta plane, so we have v, it's steady, it's a function only of of r and theta and only has r and theta components, I should emphasize that there's some subtleties you should be aware of. For example, the problem we did at the beginning, the very first problem we did today when we looked at the Hill vortex, or the Hill bubble rising, right? That was a three-dimensional flow, right? In the sense that it had, well, I guess it was a 2D flow, but it was independent of theta. So you can have a three-dimensional flow that still only depends upon two independent variables. So you could have a 3D flow, it's got a component in the r, theta, and z direction, but it only depends on r and z. So it's a 3D flow that depends only on two variables, is axisymmetric, you know. So you have to realize dimensionality has to do with the number of dependent variables you have. Dependent variables being the velocity components and the pressure. So in the problems we look at, there are basically four dependent variables: the three velocity components, and the pressure. Okay. But you can have these 3D flows that depend only on two independent variables, two independent spatial variables in time, or just two independent spatial variables. And like we had before, we had a 1D flow, the problem we did just before the pizzas came, it was a 1D flow that depended only on theta. Remember? That was the vortex. You could also have a 1D flow that could depend upon r and theta. Actually, was that true? The vortex depended only on r, right? Yeah, the vortex problem depended only on r and time. So it was a 1D problem that depended only on one independent variable. But you could have a 1D problem that depends on two independent variables, r and theta, for example. So you can have any combination of these things, is my point. Okay, so VR, in this case, is a 2D flow. And the radial, VR, so this is going to be in cylindrical, in this case, polar coordinates, because there's no flow in the z direction, it's just in the r theta plane, is a function of r and theta in the radial direction, plus v theta, which is a function of r and theta in the azimuthal direction, right? E hat theta, where VR is given by some constant m, which is a source term, but you don't need to worry about it for this problem, upon 2 pi r plus u cosine theta, and v theta, the scalar function v theta of r and theta, is equal to minus u sine theta. You should note when you look at these things that the dimensions make sense. So VR should have units of velocity. So cosine theta is dimensionless, so u has got units of velocity. Same with v theta, u has got units of velocity, sine theta is dimensionless. And that means that this thing, m over r, must have, 2 pi is dimensionless, so m over r must have units of velocity also. So this must have units of length squared over time, m does. Length squared over time divided by a length is a length over time. So m must have units of length squared over time. So you can always extract out what the units are with these things, because each term has to be dimensionally the same and equal to the dimensions of the thing on the left-hand side. Okay, so m and u are real valued positive constants. Okay, where this quantity m over 2 pi u characterizes the shape of the bluff body, and u is the magnitude of the free stream velocity in the positive x direction. So it can be shown that on a theta between pi over 2 and 3 pi over 2, the streamlines r of theta are given by so theta varies between pi on 2 and 3 pi on 2. R of theta, streamline, the equation for the streamline, looks like m upon 2 pi u sine theta times some constant c minus theta, where c is a constant that takes on a unique value for each streamline. So this is the equation for the streamlines, each different integration constant, you get a different streamline. Remember, we derived an equation, a differential equation that that was integrable, and the integration of that gave a streamline. As long as you chose a value for the constant of integration, a different constant of integration puts you on a different streamline. Same with this. So as you successfully choose different values of c, you get a different streamline. Okay, and so if you cycle through a bunch of different values of c, you'll start mapping out the whole streamline space. Okay. All right. So the first question is, determine the location of the stagnation point on the left half plane, and I'm going to call the stagnation point coordinates r, st, comma, theta, st, in the left half plane, where theta is between pi over 2 and 3 pi over 2. Okay? So that's where this equation is valid in the left half plane. So we want to determine the stagnation points of the flow. And that corresponds to where VR equals V theta equals 0. Where does that happen on the left half plane? So that means theta is going from pi over 2 down to 3 pi over 2. So in the left half plane, quadrants 2 and 3, right? Make sense? So where are the stagnation points of the flow? Okay, so we know that at the stagnation points, we have VR equal V theta equals 0. Okay? In the case of V theta equals 0, and for it to be a stagnation point, both have to be 0 at the same point, right? It's 2D flow, so both components of velocity have to vanish at the same point. You can have places where one component vanishes and the other one doesn't. That's not a stagnation point, right? So the whole velocity vector must vanish, right? So this means that V must equal 0 at that point. And in the case of V theta, we have theta stagnation. The coordinate must be what? Let's look at V theta. What's that? Right. So that's when sine theta equals 0. Oops. Sine theta equals 0, right? Which means theta equals 0 comma pi, but we are restricting ourselves to this, so that means theta equals pi. So in the left half plane. Okay, so that's one part. Now we need to find our stagnation point. So for in the case of VR equals 0, we have, where is it? It's up there. It's m over 2 pi in the case of VR equals 0, theta equal the stagnation point, because all we care about now is values of theta, which could correspond to making v theta 0. So we have to look at the case where vr equals 0 when theta equals theta stagnation, right? Otherwise, you're not on a coordinate value of theta, which could have a stagnation point for b theta. So we have, which is equal to pi. We have m over, where is it? Over 2 pi r stagnation. No, I should say this. This should actually be stagnation, right? And this should be capital theta, stagnation. Okay? But specifically, the one that we're interested in is the one in the left half plane. Okay, so similarly we have theta stagnation equals pi, m over 2 pi r stagnation is equal to, because VR must vanish, so that must be equal to minus u cosine theta stagnation. Okay, so that tells us that solving for u must, oh, I'm sorry. And what's that equal to? In the left half plane, what's that equal to? What's the cosine of pi? It's cosine of pi. Yeah, right? Because cosine is 0, right? It's plus 1, so it's minus 1, right? So this is minus u, which makes this a plus u. Does that make sense? This thing is equal to cosine pi, which equals minus 1. Okay? So now we have r stagnation is equal to m upon 2 pi u. Okay? And then consequently, the stagnation point rst comma theta st equals m over 2 pi u comma pi. So that's the r theta components of the stagnation point. Is that clear? So there's one stagnation point, it turns out, and it corresponds to, runs along the coordinate line theta equal pi, and if you go out on that coordinate line till you hit a value of r, which is equal to little m over twice pi u, that's a stagnation point of the flow. So you could think of that as kind of the front of the bluff body. That's where the flow hits the bluff body. Okay. B. Determine the value of the constant c associated with the stagnation streamline. And I'm going to call that streamline lowercase r st as a function of theta, right? So in general, the streamlines are defined by this function r of theta, which I've got up here, equation for all the streamlines. But I want you to find for me the value of c corresponding to the stagnation streamline. What is a stagnation streamline? It's a streamline that has the stagnation point on it. In this case, we only have one on the left half plane. So we need to find the streamline that goes through this point, m over 2 pi u comma pi. All right? So that means the stagnation streamline has to have this point. It has to have at least one point on it that's got theta equal pi, and another point that's got this m over 2 pi u. So, evaluating, so this is a particular value of c, so it's a special case of this streamline equation. So, evaluating RS of t R sub st of theta, I should say, at the stagnation point will allow us to solve for c, right? Because we know the stagnation streamline must contain the stagnation point by definition. So let's evaluate. Let's evaluate the r of theta. Oh, I guess I should say evaluate r. I should say evaluate r of theta at the stagnation point to find, which is m over 2 pi u, comma pi, to find the constant c so we have RSR of st of theta it's a function only of theta, right? Because it's a 2D flow in the r theta plane. This thing is equal to this thing must be equal. So basically, we want to evaluate this at the stagnation point. So there's some curve, right? And here's your stagnation point. So this guy here is RST, capital RST, comma theta st, which equals m over 2 pi u, comma pi, right? So that's RST. This equation here, this equation is RST as a function of theta. So we're going to take this general curve, and there's a bunch of different ones. This is associated with some value of CST, right? And there's a different curve over here, which is evaluated with some other C, C1. And there's another curve here, doesn't go through the stagnation point, and this is C2. This is the C associated with the stagnation streamline. Does that make sense? So we're going to take this general function R for all streamlines, and to find C, we need to evaluate it so that this streamline in order to go through the stagnation point, it must be that R of theta is equal to RST, and theta is equal to theta st. So that means that RST has got to equal this, and theta st must be equal to that, pi. So this thing is equal to capital R st, which we know is equal to m over 2 pi u, right? That's what RST is. And that whole thing has to equal the right-hand side, which is m over 2 pi u sine theta, right? What is theta? What is the sine of theta? Where is the sine of theta? Up there? It's really in the denominator. Doesn't that suck? I gave you a problem where I put 0 in the denominator. Why did I do that? All right, so we have to do this little number. Why did I do that? It's the limit as theta goes to pi, which of m over 2 pi u times the sine of theta times c minus theta, and that's equal to the limit as theta goes to pi of m upon 2 pi u sine theta c minus theta. Why? Because this sucks, right? Let's just go ahead and stick a 0 in there. Doesn't that suck for you? Sucks for me. Because if I just put a 0 in there, I've got m over 0. I want to take a limit. Why do I do that? What? Oh, I love it. Some guy says L'Hopital rule. You be that guy. Exactly. We've got to apply L'Hopital's rule because we have a 0 in the numerator, right? So it's got to, in order for this thing to make any sense, only way, that was very cool. So the only way for this to make any sense is if this thing is going to 0, it's got to be that the numerator has to go to 0. Otherwise, we got a major problem. Sine of pi cannot be allowed to sit in the denominator unless something in the numerator is checking that. So it's got to be that c has to equal what? So theta's going to pi, right? So what's c got to equal? It's got to equal pi. So that's why I put the limit in here, because I got trouble. I saw trouble with a capital T that rhymes with P and that stands for pool. You know what that refers to by any chance? No. Okay. Music Man, 1950s. It's a Broadway play from 1950s and wasn't very good. So theta goes to pi. We have a 0 down here, but if c is equal to, if and only if c is equal to pi, will the numerator vanish similarly, right? And so you'd have 0 over 0, that's an indeterminate form, right? It's an indeterminate form. So how do we resolve that? We apply L'Hopital's rule. It's an indeterminate form which can be attacked by L'Hopital's rule, right? We can take the numerator and the derivative of the numerator and the denominator with respect to theta, and that ratio is in the limit as theta goes to pi is equal to the ratio that thing, pi minus theta over sine of theta goes to. Same approaches the same limit if you take the derivative numerator and denominator, right? So similarly, if it went to infinity over infinity, that's another kind of an indeterminate form that L'Hopital's rule applies to, right? In this case, it's got to be 0 over 0. So I hope that you didn't lose that, but I think you're going to see in just a minute what is going on. Okay? So essentially, we would say that this, I'll just write it over here. This thing tends toward 0 over 0 if and only if, if and only if c equals pi. Otherwise, the limit approaches infinity. Has to be that c equals pi. Now, some other students did something a little differently. They multiplied the whole equation. They saw this, didn't like it, so they multiplied the whole equation through by 2u sine theta over here. Okay, and so the 2u canceled, and you get m sine theta equals c minus theta. And they said, they were really smart, right? When they did that, I thought that was really clever, but that's a perfectly legitimate thing to do, right, is to multiply the whole equation through by this thing that's blowing up and say, okay, so this thing times sine theta has to equal c minus pi. What does that for c? If sine theta is pi, c's got to be pi. So if sine theta is equal to sine of pi, it has to be c equals to pi. So that's another way to look at it, too. There was nothing wrong with that. I saw it, and I said, geez, these guys dodged the L'Hopital rule bullet, and everybody else just got shot by the L'Hopital rule bullet. No, a few people got this right. I don't remember how many, but it's a little tricky. I must have been in a bad mood or something. I don't know what. I just thought it was so cool to put a L'Hopital rule, bring L'Hopital's rule into this thing. Nobody else agreed with me except one guy. One guy by the name of Aaron Colby, who later went on to be a teaching assistant for this class. And he took this class in 2009 or something. He was sitting in your seats. And he came back to me after I took that exam, and he said, how cool was it that you gave an exam where we actually had to apply L'Hopital's rule? And I thought, I guess that was really cool. I think you're probably the only one that thinks that. He went on to be a teaching fellow for this class 2 years in a row. But he really just thought that was so clever. So applying L'Hopital's rule. So we're basically what you want to see is applying. So we have now m over 2u m upon 2 pi u is equal to the limit as, what did I say? Theta goes to pi. Theta tends toward pi of, now we're going to say c is equal to pi. So that's pi minus theta upon 2 pi u. Oh yeah, that's fine, okay. M over 2 pi equals, m, oh yeah, I have the m over 2 pi u. Let's pull that out in front, folks. I'm sorry about that. Let me put that out in front. I'm going to factor out the m over 2 pi u because it's just a constant times the limit as theta tends toward pi of pi, which is now what c must be. You could basically say that c must be pi and you could stop right there. You don't actually have to apply L'Hopital's rule. But just to be totally anal about it, let's get the whole problem done and apply L'Hopital's rule and show that this makes sense. Pi minus theta upon sine of theta. So this m over 2 pi cancels on both sides of the equation, and we get 1 equals the limit as theta tends toward pi of pi minus theta upon sine of theta, right? And so what does that go to? So whatever this limit goes to, it's the same as what, oh, right. So now we've got this indeterminate form. This equals, what does this equal to? 0 over 0. Does everybody agree with that? So if theta, as theta goes to pi, you get 0. As theta goes to pi, you get 0. So we haven't proven yet, technically speaking, that c is pi, but we've said that the only value it could possibly be for us to make any progress is for c to be equal to pi. Does that all make sense? Now we're just checking to see if it does. And so in order to really check your work, you need to test it. So now you apply L'Hopital's rule. How does he spell his name? He's a guy with an apostrophe in his name. Everybody see what I did here? Does it all make sense to you guys? Did I lose anybody? I chose a value for c that allowed us to make progress. Any other value of c I chose, the thing blows up. There's no other value of c you could choose for which you could have a bounded solution on that stagnation streamline, right? On the streamline where theta is equal to pi. Okay, so applying L'Hopital's rule, we see that 1 equals, well, I'm going to go down here. The limit as theta tends toward pi of pi minus theta over sine theta. Well, that's got to be equal to, according to L'Hopital's rule, the same limit by taking the derivative of the numerator with respect to what? Theta, and the derivative of the denominator with respect to theta. That's what L'Hopital's rule tells us. Right? So this has got to be equal to d by d theta of pi minus theta over d by d theta of sine of theta. And that's equal to the limit as theta, this shouldn't be a pi, 0, this should be a pi. As theta tends toward pi of, what's this derivative with respect to theta? Minus 1. What's downstairs? Cosine theta. And what is that equal to in the limit as theta goes to pi? It's minus 1. When cosine theta is? Minus 1 over minus 1. And we check, because the whole way back here, it's got to equal 1, right? So now we see that indeed, not only is there only one value c can assume that would keep this thing bounded on theta equal theta equal pi, but indeed it does remain bounded, and L'Hopital's rule proves that. No reason at all, except that I saw this is the way to solve the problem because I always try and find the simplest way to solve the problem. Alternatively, so you don't have to use L'Hopital's rule at all, right? And I saw a few students do this, and I said that was even cooler because you didn't have to use L'Hopital's rule. Alternatively, we could say m over r s, what did I say? Oh, over 2 pi u. Alternatively, we could multiply by and I'm going to say star is this equation over here. I'm going to call that equation star by 2 pi u sine theta. And you get m over 2 pi u times 2 pi u sine theta is equal to wait a minute, m over 2 pi u sine theta. Oh yeah, I could multiply by 2 pi u sine, that's a 10 pi, yeah, is equal to m times c minus theta. And the m's cancel on both sides, 2 pi u cancel on both sides, and you get sine theta is equal to c minus theta, which is, of course, 0. Yeah, so sine pi, and I should put st here. All this should be st, right? So then you have sine of pi is equal to c minus pi. C must equal to pi. A little simpler. But either way, it's correct. I just think the L'Hopital's rule is kind of neat to see that. I think Aaron used the L'Hopital's rule, but I don't know who else did. How many people did that? I think more than one, though. But I've never put that on another exam. I just show it to you guys every year. I teach this class. Either way works. But it gives you all the confidence in the world that L'Hopital's rule continues to work all these hundreds of years later. All right, so what's next? That was a part B, right? Was that B? Yeah. So now C is equal to pi, and I guess to sort of finish this, I think I'm going to leave this one up here because this has got the problem statement on it. Thus, the sort of to finish the point, well, c equals pi. That's really all that was asked for. And r st of theta is equal to m upon 2 pi u sine of theta times pi minus theta. So this is valid on theta between pi over 2 and 3 pi on 2. Okay? So that becomes the actual equation for the stagnation streamline. That wasn't really asked, I mean, that wasn't technically asked, but that's what the equation is. All right, so the last part, C, says neglecting gravity, determine the because now we're flowing in the r theta plane, so we're not, this is neglect gravity. Determine the variation in pressure P theta along the stagnation streamline, RST, and express it in terms of some stagnation pressure P naught. So neglecting gravity, determine P of theta along RST of theta, the stagnation streamline, where P naught is the stagnation pressure. And what can you say? What is the stagnation pressure? Can you remember? It's the pressure at the stagnation point, so it's the pressure when the velocity vanishes. All those points in the flow field where the velocity vanishes are stagnation points, and it's the pressure at those stagnation points. So it's the pressure corresponding to all those points in the flow field where the velocity vanishes. What also can be said about the stagnation pressure? It's a maximum pressure in the flow field, right? All the kinetic energy has been converted to static pressure at that point. All the kinetic and potential energy, but in this case we're neglecting gravity. So all the kinetic energy has been converted to static pressure. So it's the maximum pressure in the flow field. Good. So neglecting gravity, determine P of theta along with... So how do we get the pressure? Why Bernoulli? Right. So it's limited. We're limiting the flow to an inviscid, incompressible, steady flow. Okay. So, since the flow is steady, inviscid, and incompressible, the Bernoulli equation applies. Neglecting gravity, we have P naught plus 1/2 rho V naught dot V naught is equal to P of theta, R and theta, excuse me, plus, oh, this is, this is P of R ST of theta. Everybody agree with that? It's a Bernoulli equation if we neglect gravity at 2 points on the stagnation streamline. And this is valid along the stagnation streamline. Defined by R at sub ST of theta. Okay, that's true only along that stagnation streamline. It's not true everywhere in the flow field. But I should emphasize that to make sure that we're on the stagnation streamline, we have to make sure that wherever you see R, you're applying RST, this equation here. Okay, so wherever you see R, it's really this thing that is being evaluated. And notice this thing depends only on theta, obviously, because it's showing you how far you are from R equals 0 along the stagnation streamline as a function of theta. Okay? When theta happens to hit pi, you're at the stagnation point on that streamline. But for any other value of theta, you're at, you know, you're at You're on the stagnation streamline, but not on the stagnation point. Okay, and the pressure is going to vary along that stagnation streamline according to theta. But you're constrained to move only on those values of r that are determined by this function here as you move with theta. So r is locked in lockstep with theta. So you can't just move theta and choose any r. Whenever you change theta, your r varies in accordance with whatever that new theta is, and that's where you are on that streamline. And as you continue to move theta, it redirects you along r, and that's just tracing out your stagnation streamline. When you evaluate the pressure as a function of r and theta, you're substituting for r this value of r of s and t. Does that all make sense? So we have to make sure that if we're to guarantee that we are along the stagnation streamline defined by r of s and t, we have to evaluate r at r of s and t. Is everybody clear? I talked about this earlier when I did an example of flow over the cylinder in cross flow. Do you remember that problem? And I said, let's look at the pressure on the stagnation streamline. I replaced r with rst. Okay, so what do we know about this term here? It's 0. Why? We're at the stagnation point. So this is 0 because we're at the stagnation point. Okay. So now what we have is P naught, which is a maximum, right, minus P of r comma theta is equal to 1/2 rho v at r st theta dotted with v. Okay? And that dot product, because v is equal to vr in the e at r direction plus v theta in the e at theta direction, this is equal to rho upon 2 times vr squared at r st of theta plus v theta squared. Okay? And that is equal to rho on 2 times, well, what is r st? It's this thing here, right? M over 2 pi u sine theta, pi minus theta. And so let's square it. Oh, I'm sorry, that's what the stagnation, I misspoke. That's what RST is, but VR is way up here. This is VR. So evaluate VR at RST. So wherever you see RST, replace it with this mess. We're not going to do that. We're just going to call it RST and remind ourselves that this is what it is. Okay? So what is VR squared? So this is equal to m, help me out here, m over 2 pi RST plus u cosine theta, thank you, quantity squared. And what's v theta? So that's plus u squared sine squared theta. And we're done. So you can manipulate this if you want. I don't really see that. There's a cosine squared and a sine squared theta. You can expand this out, and that will give you a 1, a u squared cosine squared sine squared theta. So one can show this is equal to rho upon 2 times m over 2 pi RST squared plus mu over pi RST cosine theta plus u squared, where RST is equal to m over 2 pi, m over 2u sine theta times 1 minus theta over pi. That's it. So if you want, you can plug this in here if you care to, but you don't really need to. Square this and put it in here, or and then put this in there. But this is fine. And what did I subtract? You've got some furrowed brows. Oh, I have a pi here, so I factored out a pi. Pi cancels here, so you get a 1 over theta over pi. Didn't really need to do that. I have no idea why I did. I think I do know why I did that, because I took the next step and I substituted this in here and here, and I still don't know why I did that. Anyway, you don't need to do that. It's just annoying. An annoying little thing to do.
Foiling, don't you?
What's that?
Doesn't it eliminate the term when you have to foil the...
Over here, maybe? Because you have an mu cosine over sine, zeta cotangent. You still have a pi down here, though. Is this the one you're talking about? I don't know. It doesn't matter. It's the same answer. You know, I love when I look at my kids' math tests and they say, you know, it's like, you know, 3/2 isn't the same as 1.5 in these guys' minds. I don't know why. Got that wrong. Should have written 3/2. No, I got it right. 1.5 is unambiguously 3/2, you know? So, anyway, it's fine either way. So, but I think it's really important to emphasize that when I ask you for the pressure along the stagnation streamline, R is no longer an independent variable. And we've talked about this before. We did that example in class with the flow of the cylinder and cross flow. And you had to, you know, establish, in order to enforce this statement, that this pressure is along the stagnation streamline, you have to enforce that R is being evaluated along that streamline, which varies like R sub st. All right, this next problem, I think I threw my arms up one night when I was trying to write an exam, and I was running out of time, and I got desperate, so I pulled a problem out of some book. And they're never as good as my problems, I think. And so it's really short and easy. And I only made it worth 20 points. But I was getting kind of desperate, so I made a real simple problem. But let's just do it, unless you don't want me to. It's this recall for a steady flow of an inviscid fluid we found from the conservation of momentum, this equation. And here I'm asking you, if the fluid's an ideal gas, derive an expression for the variation of pressure along streamlines for an isothermal flow. Did you guys do this problem in homework? So this is problem spring 2009 number 3. Shall we do that one? Yeah, I guess you didn't do that problem in homework, so we should just do it, right? Oh, by the way, are there any other further questions about this problem? Does it all make sense? How's this material seeming to you guys? Reasonable? Feeling some confidence now? Bubbling up? What's that? Yeah, I know. But then go home and do it without looking at any of this stuff. Just do cold turkey. Just one day, like Saturday or Sunday, just sit down and knock off these problems without looking at your notes and see if you can do them. Okay? Without looking at it, see if it makes sense. Because at this point, I'm just going to be giving you another variation on a theme. That's what you're going to see, because this is all we've learned. I think with every other class, maybe, I know Raj, we're not sure about Raj's semester, but I think most of the other classes I went all the way through linear momentum and sometimes linear conservation of energy for exam 1. I'm not quite sure how I did that. It must have been very stressful for me and everybody else to have packed all that material in the same amount of time. So you guys are just getting less stuff in exam 1, which of course makes exam 2 a little more painful. There's more in there. Things to look forward to, things to be cheerful over. This is spring 09. Number 3. So, for steady flow of an inviscid fluid, we have dPdS plus rho v dVds plus rho g dzds equals 0 along a streamline. Okay. So, S is the streamline coordinate, right? And we derived this in class. It's just that in class, we only looked at the special case where rho was constant. Remember that? So if rho is constant, we can integrate this equation along the streamline. Because we could write this thing, v dVds, as 1/2 d by ds of v squared. Remember? We did that little exercise in class. And d by ds of v squared is an exact differential. So if rho is truly a constant like g is, then you'd have, and you multiply the whole equation by ds, you'd get dp plus rho, 1/2 rho, times d by ds, or d of v squared, plus rho g dz. And that whole thing, each one of those terms is term-by-term integrable. They're exact differentials. And we integrated that along a streamline, and we got the Bernoulli equation, right? Which was p plus 1/2 rho v squared plus rho gz is equal to a constant along the streamline. That's how we got the Bernoulli equation. We came to this equation, which was the linear momentum balance along a streamline, and resulted in the Bernoulli equation when we considered only an incompressible fluid. So what we're going to do is something different. If the fluid is not incompressible, but rather an ideal gas, derive an expression for the variation of pressure, the variation in density along streamlines for an isothermal flow. Sounds like a thermodynamics problem, but it's not. I mean, it is, I guess, but this is really, this is basically solving this fluids problem. So, a fluids problem for an ideal gas. So if the fluid is an ideal gas, then P equals rho RT. Okay, remember that? R is the gas, the ideal gas is the universal gas constant. And for an isothermal process, what do we know? Right. T is constant. And dPdS, take a derivative of that thing, with respect to S, is equal to RT times d rho ds. Does everybody see that? So if we have an isothermal process, then T is constant, universal gas constant is certainly constant. So dPdS equals d rho ds times this constant RT. So the pressure, for an ideal gas, the pressure varies in direct proportion to the density, where the rate of change of pressure varies in direct proportion to the density, where the constant proportionality is just RT. Okay. Thus, where do you see dPdS over here? We have RT times d rho ds plus rho times
v dv ds plus rho g dz ds equals 0 along a streamline. Okay? Dividing by rho, which never vanishes, so we can do that. Right? Otherwise, we violate the continuum approximation. So we can divide by rho. What do we get? We get RT times 1 over rho d rho ds plus v dv ds plus g dz ds equals 0 along a streamline. Now, noting that this is the same thing as d by ds of 1/2 v squared, we have RT 1 over rho d rho ds plus 1/2 d by ds of v squared plus g dz ds equals 0 along a streamline. This is a logarithmic derivative. Does that look familiar? Right? If we were to multiply this whole thing by ds, we get the integral of d rho over rho. That integrates the natural log of rho. It's called a logarithmic derivative. Integrate this thing, you just get, multiply by ds and integrate it, you get exact differential, it's v squared. Multiply by ds and integrate it, you get g times z. Right? So it's exact differential. So this is equal to RT. I guess I can just do it that way. Multiplying by ds and integrating along a streamline we get RT times the integral of d rho over rho plus 1/2 integral of dv squared plus g times the integral of dz equals constant. Well, I guess after the integration, right? So this is equal to 0. Is that right? The integral equals a constant along the streamline. The integral equals a constant along the streamline. But we want this to be an exact differential, right? So what is this equal to? It's a logarithmic derivative. It's the integral of d ln rho plus 1/2 integral of d v squared plus g integral of dz equals constant along the streamline.
Since the constant is already 0, can't you say it's still 0?
Huh?
Can't you say the constant is 0 because it was already defined as 0?
It's not, because the differential equation is 0. But once you integrate it, you've integrated it up. And this integral is equal to, this thing here is equal to 1/2 v squared. So that's after integration. So it generates a constant after you integrate it. Does that make sense? Yeah. But we can just write this as v squared over 2. We can just write this as z times g. But do you guys see how this d ln of rho is equal to d rho over rho? You don't see that? Okay. Let's call this d of u of x. Do you remember this? The derivative of the natural log is just, right? The derivative log of x is just 1 over x. The derivative of the log of u of x is equal to 1 over u du dx. It's chain rule, right? Right? We all know that. But but instead of being x, suppose it's a function of x, then we have to apply the chain rule. And that's right, because rho is a function of the streamline coordinate. Right? Rho is a function of s. So we have d rho, where rho is a function of s, over rho of s. So we have to write this as an exact differential. So we have to recognize that d by ds. So I guess I should say, to put it in our variables, d by ds of the natural log of rho of s is equal to 1 over rho of s times d rho ds. Everybody agree with that? Can you guys read that, or is this thing in the way? This is okay? This is all visible here? Oh, wow, it's amazing. I don't see how you can catch these angles, but so does that make sense? And so that's what we've done over here. And now we've got exact differentials. And we can integrate it. The problem's done. So we get RT, is equal to this stuff, right? So that means that RT times ln of rho plus v squared over 2 plus gz equals a constant along a streamline. And this is a perfectly legitimate solution. You can actually solve for natural log of rho if you want and exponentiate it. And you can solve for ln rho. You could say that there's no reason to do this, but we'll just put it up here if you want to see it. Ln rho is equal to minus v squared over 2RT, right? Because you have to divide through by RT. And then we have plus GZ plus a constant and if you want you can exponentiate that. So take exponentiate both sides and you get rho is equal to I can factor out an RT is equal to K times E to the minus 1 over RT times V squared over 2 plus GZ along a streamline. So this is any one of these things. This is also another way to write it, but any one of these things in boxes is fine as far as I'm concerned. What's that? That's right. So basically, e to the c is a new constant, right? Oh, I see. It should be here. So let's call this k. That's okay. So let's call this thing a, right? So a is equal to c over rt, right? I'll just call it C over RT. It's just some new constant because it's an isothermal process. And now we have, when you exponentiate this thing, you get e to the this plus that, which is the same thing as e to the this times e to the that. So e to the C over RT equals K. Does that make sense? It's just a new constant. I just lumped a bunch of other constants together into a new constant. So that pre-multiplies e to the CRT pre-multiplies this whole exponential here, so I'm just calling it K. Yep.
On the exam, if we were to skip the step where we found the exact differential for rho, would we lose points?
What do you mean skip it?
So, I mean, so say we just went from RT times the integral of d rho over rho, and then right to the bottom part.
Right. You need to show us that this is, because this thing is a function explicitly of S.
Right.
So you do need to show us, you need to do this to show us that this, reduce it to an exact differential by using that. I mean, it's technically right to go from here to here, but I want to see that step. But you wouldn't lose much if you just went from here to here, but I would like to see this intermediate step to show me that you know that rho is a function of, I mean, it would be nice to see this in the margin, you know, and then you'd say, ah, I see. So d of the ln of rho is equal to 1 over rho d rho. That's what, you know, just something like that in the margin helps us. Understand? You realize that rho is a function of S and you've used the chain rule. Because to get at this result, this 1 over rho d rho, that's the chain rule that you're applying, right? And so that tells me that you know that rho is a function of another variable. But that's a pretty simple problem. Yes?
Your second line on the bottom board, you have the 1/2 dds v3. I'm not with this direct combination of how you...
If we go from here to here?
Yeah.
So the question is, how do we go from here, v dv ds plus to 1/2 d by ds of v squared? Yeah. It's the chain rule also. So work it backwards. So I guess I'll go over here. So we're saying that 1/2 d by ds of v squared equals 1/2 d by ds of v times v. I'm not going to put a dot there because it's not a dot product. These are scalars. This is the scalar component of the velocity along the streamwise direction. It's the vs component. Okay, so this is, you can think of this as u times v. So now I'm going to apply the product rule. First times the derivative of the second, plus the second times the derivative of the first. So this is equal to 1/2 first times the derivative of the second, v, d by dv ds, plus the second times the derivative of the first. Right? It's actually the product rule, not the chain rule. This is the product rule. Do you see what I did there? First times the derivative of the second plus the second times the derivative of the first. Add them together plus 1/2. Well, these are the same term, so it's just equal to v dv ds, right? Because this plus this is twice v dv ds, which cancels the 1/2. And so now you see that this thing equals this. But the nice thing about this is it puts it in the form of an exact differential. And we also did that in class, you may recall, when we derived the Bernoulli equation. We came across this kind of a term here that we derived from kinematical principles. And then we said, oh, let's write this in a different way. Write it kind of like a kinetic energy term or a differential of it. And there was another question over here, I think. Oh, same question. Okay. Okay. So now we've knocked off like 5 or 6 problems. I don't know. What? 5. All right. Can I skip? I'm going to leave this problem to last, this next one. Is that okay? You can't read it? Is it too small to read? But you guys have like superhuman eyes. What? Oh, because you have the reading glasses, yeah. But people without reading glasses can't read it either? You can read it? Okay. Oh, when they upload the solutions? Yeah. Okay. Because I can read it. Why am I able to read it and I'm like twice your age? I'm more than twice your age.
Well, it's missing a picture.
It is?
Yeah, it says in the figure below. There's a figure below.
Oh, why is that? Why is it missing a picture? Do you know? All right, well, I can draw that picture. Let's leave that to last. We only have sugared water, huh? I'm really thirsty. Dehydrated. All right, I have to go back to my office and get something to drink when I leave. Oh, to my office? Oh, yes. Thanks, Roger's thinking, I'd like to get a little exercise. This is really painful. Thank you. What are you looking at? How much battery you have
I have
left?
to reset this every 20 minutes, which is a pain in the ass.
Oh, and you So we have let's do this little cross product, this little exercise. So this is V cross dr is equal to this determinant, which is equal to VR V theta Vz dr Rd theta dz. And that equals, well, we know this is 0. Right, that scalar is 0. So we get E hat, in the E hat R direction, you get 0. Is that right? Here we go. Oh yeah, and R d theta. So there's no change in theta, right? So this thing is axisymmetric. So this does not show up. This is just 2D. Right. So there's no change in theta. I guess it's axisymmetric, basically. So there's no dependence on theta, okay, in this problem. So we have E hat R, this cross product is 0. E hat Z, this cross product is 0. And E hat theta, we get this and this product here minus this product here. So we get E hat theta times VR times dz minus Vz times dr. And that whole thing has to equal the 0 vector. R d theta, so there's no dependence on theta. If it's axisymmetric, there's no dependence on theta. Okay? Yes, so it would you certainly don't have any dependence on that. So you wouldn't have, basically you have, all the flows in the xy plane, the cross product is perpendicular to that in the E hat theta direction, and there's no theta dependence. So that product would, let me just see here. We've got right. So then you'd have because it's flow in the 2D plane. You think about the right-hand rule. So you have V is in the R theta plane, and dr is in the R theta plane. Right? Excuse me. The vector V is has a component in the radial direction and the z direction. So it only has components in basically the RZ plane. dr doesn't even exist in the dr doesn't have a component in the theta direction, right? So remember, I don't know what I'm saying here. How do I word this? This is dr has no E hat theta component. So how do I say that? It's I mean, this term is gone, right? Because it's this thing here. So I'm just populating what is VR and this thing here, right? So there's a VR component, 0 times E hat theta, and a VZ component. VR, 0 times E hat theta, and a VZ component. Here you've got a dr in the radial component, 0 in the E hat theta direction, and dz in the E hat z direction. So there's a 0 there anyway. This is just the general vector for the 3D cylindrical coordinate cross product of V cross dr. But this is 2D, the RZ plane, RZ plane only, 2D plane. So this is because of 2D flow, right? so the dr vector lies in the rz plane, and the velocity vector has components only in the rz direction, right? So consequently, when you take the cross product of those two things, v cross dr is in the theta direction. So you can only have a theta component. And that's because this is a 2D vector and this is a 2D vector. So the reason these things are 0 is because it's 2D. So it's 2D flow, and we only have flow in the 2D in the r theta plane. So that you only have an e hat r and an e hat z direction in the position vector. Position vectors all lie in the rz plane. Does that make sense? Okay. So that means the cross product of two vectors that lie in the same plane is a vector orthogonal to that plane. The two vectors both lie in the rz plane. The cross product of that is in the theta direction. And that's with these two things 0 because they're both 2D vectors. You're left with only an e hat theta component. That vector must be equal to this vector, and therefore, which only has a component in the theta direction, which means that the scalar projection of that in the theta direction is this thing here, and that must vanish. And so consequently, this tells us that VR dz must equal Vz dr for that to be generally equal to the 0 vector. And writing this thing in differential form, because we want to solve for the differential equation dr dz, dr dz is equal to Vr over Vz. And that's equal to, from the Hill solution, that's equal to u over r squared, shows up as a coefficient to both of those Vr and V theta terms. So if you take the ratio of this Vr to this Vz, there's a u over r squared coefficient, so that cancels out. And we get Rz upon big R squared minus little z squared minus 2 little r squared. Thus, along a streamline, r equal r of z, remember? So we're on a streamline now. So that curve in the rz plane, it's traced out by r, varies only with z. So r of z must satisfy the following ODE. dr dz is equal to r of z times z all over big R squared minus z squared minus 2 r of z squared. And I want to see you write this in terms of r of z so that you know that this is an ordinary differential equation where r depends only on z. It's not something I think you guys are going to be able to integrate real easily. So I didn't ask you to. But that is the equation for the streamlines. If you it's first order, right? dr dz, but it's nonlinear. You've got an r squared down here, and it's in the denominator, and you have an r in the numerator. So it's a nonlinear equation. So you can numerically integrate these to get streamlines of the Hill bubble problem. And if you were to numerically integrate those things, you would get you'd get this, remember the sphere I drew at the beginning of class? You'd get these kinds of streamlines. Oops. Yeah. Something like that. So you get this circulating flow in the sphere. You can think of this as an air bubble floating up through a liquid, and you'd be getting these convection countercurrents going on inside this little air bubble. And those streamlines lie in the RZ plane. At every theta, you have the same streamlines, but you'd have different ones. You'd have another one here, have another one here, right? And so when you integrate this, it's first order differential equation, you integrate it up numerically, you would choose a constant, you'd give the constant of integration that's generated from that numerical integration, you'd pick a constant and you'd get one of these streamlines. Then you'd pick a different constant, numerically integrate it, and you'd get another curve. Does that make sense? And if you just integrate this thing numerically and choose different C's, you'll get all these different streamlines. And they apply at each one of these little planes, right? Each one of these little planes. And you could think about this if you were to like look down on this circle here. You could look at it like this. And the convection currents are flowing around like this, and on this one face they're flowing around like that. Every one of these pi faces you have this solution. Does that make sense? It's a very cool solution that he came up with. And this, you can numerically integrate that equation quickly and easily in something like MATLAB or Mathematica and generate all those streamlines and see how it looks. But it looks something like this, convection currents. Okay, what's the next question? B. Oh, it's a totally different problem. Derive ODE governing the streamlines lying in the r theta plane. It's kind of the same. Want me to do it? There's no need to do it, right? I mean, it's really straightforward, except now it's in the r theta plane. And, you have v hat r. I'll just write the determinant looks like this for the second problem. I'll just write the determinant and I'll skip all the steps. You have e hat r, e hat theta, and e hat z. This is a different flow field. This is it's a solution of sphere of radius r held in stationary, steady, and viscid incompressible flows. This is a sphere in a cross flow. Remember we did the cylinder in a cross flow problem? This is a sphere. So it's in spherical coordinates. So you have a different velocity profile, but v phi is 0 in this case. There's a v theta and a v r component. And you have v is equal to vr e hat theta plus v theta e hat theta. And v phi is equal to 0. It's identically 0. And so you have an e hat r, e hat theta, e hat, not z, e hat phi. But remember, dr is equal to dr e hat r plus r d theta e hat theta. And there's no d phi. So you'd have a plus d phi, you'd have plus r sine theta d phi. Remember that? I had erased it a minute ago. E hat phi. But this is only in the r theta plane. So you would have, it's a 2D flow, and you would have VR, V theta, and 0. And here you would have dr, r d theta, and then instead of r sine theta d phi, you'd have 0 here, because this thing only lies in the r theta plane. Okay? And then I've given you VR and V theta. And then you can take this cross product and it would be in the e hat phi direction. So you get, this whole thing would equal e hat phi times VR r d theta minus V theta dr. And that whole thing should equal the 0 vector. Make sense? So it's just like this problem, except this is, it's a spherical coordinate problem. Oh, should be, sorry. This should not be e hat theta, that should be e hat r. And then the phi component is 0. Thank you. Thanks for catching that. But the equation, you want me to write the answer? I don't need to give you the answer because you're going to get it tonight. Okay, so you carry that all out and you get another differential equation, first order differential equation like this in dr d theta. Okay? Good. Okay. So, but there's a second part to that. So let's do that part. The second part to that is Neglecting gravity, determine the variation of pressure along the portion of the stagnation streamline that lies both upstream and downstream of the sphere, and along the portion of the stagnation streamline that lies on the surface of the sphere in the r theta plane. Okay, express both pressure distributions in terms of the stagnation pressure. Shall we do that? You want to see that one done? I think we have an hour and a half. I think we can get through this one. So I only have two more after this one. We've got the one with no picture. And then we've got the cylinder problem, which I think we've done. Did I do the cylinder problem already in class? I mean, yeah, I think I did the cylinder in crossflow. Oh, no, but this is a momentum flux problem. Okay. So oh, no. Whoa, no, wait a minute, guys. This is the killer problem at the end. We got to do the killer problem. We got. Yeah, this is worth spending. It's a hydrostatics problem. Yeah, it's worth spending some time on that one. Okay, so yeah, let's do one more problem like this, and then go right to the hydrostatics problem, and that leaves two left. I like it. Okay, so I am just going to write this down really quickly. So from this comes so along a streamline r of theta, rather along the streamline r of theta must satisfy the following ODE. So after you do that you do this little cross product for part B. And I should have put the velocity field down. What's it look like? Is it a mess? No, it's not too bad. It looks kind of like this. 1 over r dr d theta equals minus 2 times 1 minus r cubed over little r cubed all over 2 plus big R cubed over little r cubed becomes a cotangent of theta. So this is the answer. This is the equation. This is the governing differential equation for the streamlines for a sphere in a cross flow. Okay? Where, and I'm going to write the equation, the velocity profiles down, where V is equal to VR E hat R plus V theta E hat theta and VR equals capital U, the velocity of the free stream, times 1 minus r cubed over little r cubed times cosine theta, and v theta, I'll say v phi equals 0 identically, and v theta equals capital U, or rather minus U on 2, times twice, 2 rather, plus r cubed, big R cubed over little r cubed, times sine of theta. Okay, so this is the velocity field for a sphere in a uniform cross flow, where way upstream of the sphere and way downstream of the sphere is a uniform flow in the x direction of capital U, in the E hat x direction. And this is what the three components of velocity look like. And the streamlines of that flow are obtained by solving this nonlinear differential equation for different values of the constants of some constant of each of the constants of integration, or the constant of integration that comes from that numerical integration. So you numerically integrate. Well, you'll anchor yourself somewhere, and where you anchor yourself, you'll integrate along that streamline, integrate this curve up, and you'll get one streamline. And then you'll go to a different point, and then integrate from that point up, and you'll get a different streamline. And you'll just keep moving along throughout the field, and you draw all the streamlines for this velocity field. So that comes from taking this cross product and using these velocity components in the VR and V theta components that come from that cross product. And then the next question is neglecting gravity. This is an inviscid, steady, incompressible flow, this velocity field that comes from that. Neglecting gravity, determine the variation in pressure. P of R and theta. Along the stagnation streamline. Along the straight, which would be P of R, comma, theta equals 0, comma, pi, and curved segments of the stagnation streamline. Okay? Okay, so now I want to take the stagnation pressure as P naught. Moving right along. So, for steady, or I'll say for this steady, inviscid, incompressible flow, the Bernoulli equation applies. It applies for any steady, inviscid, incompressible flow, but this one happens to satisfy that condition, so the Bernoulli equation applies. And taking P naught to be the stagnation pressure, we get P naught plus 1/2 rho V naught dot V naught. We're neglecting gravity, right, up here. So this is flow in the R theta plane. There's no gravity in this problem. Is equal to P of R and theta plus 1/2 rho V dotted with V along a streamline. Right? That's the Bernoulli equation, neglecting gravity. What's V naught? Why? Stagnation point. So this guy is 0. stagnation point. So we get P of r and theta is equal to P naught minus 1/2 rho times V dot V, which equals P naught minus 1/2 rho times VR squared plus V theta squared along a streamline. Agreed? So this is just a dot product of that thing there. You see where V is equal to this? So take the dot product of this thing. Notice there's no R V theta E hat theta. Don't do that. That just ruins the world, right? Because you've got velocity, units of velocity, and R V theta would have units of length times velocity. That's awful. There's no R there. Okay, that's only in the dr vector that we see that the curvilinear coordinate manifest itself there. Okay, so there's that, and I think I can. I'm going to erase this board so that I can get all 4 of them up there. So that tells us that P of r and theta is equal to P naught minus 1/2 rho u squared, capital U squared, because that factors out of both VR and V theta. There's a u in front of that, and we have a 1/2 rho, so we have a 1/2 rho u. But we're squaring VR and V theta, so the u squared comes out. We get this messy thing. 1/2 rho u squared times 1 minus r cubed upon little r. Oh, and this is on the stagnation point, so we should call this RST. On the stagnation streamline, rather. So this is r cubed stagnation, ST, quantity squared, cosine squared theta, plus a quarter, 2 plus r cubed over r stagnation cubed, times sine squared theta, like that. So did I do that right? Yeah, I think you're right. I think this should be squared, right? So let's see if I've got that right. So 1/2 rho u squared, 1 minus r cubed over r stagnation squared, cosine squared, yep, 1/4, 2 plus r cubed over little r stagnation cubed squared, yep. That look good? So this is how the pressure varies on that streamline. And now you have to consider segments of it, right? So on the upstream and downstream segments, what do we know? The straight segment approaching the sphere and the straight segment receding away from the sphere. What do we know? Theta equals 0 and pi. And what about on the curved portion of the stagnation streamline? Little r equals big R. That's exactly right. So straight segments of streamline, theta equals 0 comma pi, and p of r comma theta equals 0 or pi gives the same answer, is equal to p naught minus 1/2 rho u squared times, so what do we have here? We have theta is equal to 0, that's a 1. Theta equal pi, that's a minus 1 squared. And we lose this term, and you just simply get this. 1 minus r cubed over rst evaluated at theta equal 0 or pi cubed. I think what I'll do is this. And this whole thing is squared. Did I do that right? Yeah, because this ratio is cubed. That's good. And that whole thing is squared. That's good. And this is on for RST greater than or equal to R. Right? So this flow doesn't happen inside the sphere. It's for flow outside the sphere, right? So R has to be bigger than greater than or equal to capital R. And on surface of sphere, the curved segment of the streamline corresponds to R equal big R. And we get P of big R this should be RST, folks. Make sure you correct that. RST equal big R, comma, all values of theta. And now, this term is 0, right? Because 1 minus 1 vanishes, but that term survives. So you get, this becomes 1, and you get 3 squared. So then you get, this is equal to P naught minus 9/8. Weird of a number as that is, that's what it is. Rho u squared sine squared theta. And here, theta goes between 0 and pi, because in spherical coordinates, theta varies between 0 and pi, phi varies between 0 and 2 pi. So here are your answers. Here's the first part of the segment, and here's the other part of the segment. Okay. I think what I'd like to do, this next one's pretty straightforward, but it's a little different from what I did in class. It takes the same solution I did in class, which was the flow of a cylinder and cross flow, but then I chose a particular control volume around that cylinder and asked you to show that the conservation of mass is identically satisfied. Okay? So we did a problem like that earlier today. So I think what I'm going to do is jump to the hydrostatic problem. Are there any questions about this, first of all?
How do you, I think about a question, like, would it be the same for the top and the bottom of the sphere?
Yes. Well,
so would you change
Oh.
the equation so it's not like only between 0 and pi, like plus or minus pi or something? If it's the same on both sides.
actually, hold on just a minute. How is the problem worded? Just bear with me for a second. Yeah, so So you've got the sphere like this. You've got the streamline doing this and going around like this. And here's your sphere. And you've got that's theta. And so it's this streamline here or this streamline here is the straight segment. That's one here. But down below, theta is going from 0 to pi. So that's this top segment. And if you wanted to go from pi, actually, yeah, that's right. It's from pi, how does that work?
Is it because B is like doesn't really matter, so it's kind of the same around?
It's symmetric. It is symmetric, so you'll get the same answer. But I'm just trying to think here. Phi, yeah, phi is, yeah, right. This is the theta coordinate. So this is actually, this is looking down on it from the North Pole, right? So phi just goes from 0 to pi. Phi goes all the way around from 0 to pi, whereas theta goes from 0 to 2 pi. So we've just taken one of these streamlines around like that. But you could have taken another streamline that goes around the sphere like this. Right?
It's because it's the same answer, just on a different rotation.
Right.
The
Right.
rotation.
Exactly the same answer because it's symmetric. Okay. And then and then what I'd like to do is the hydrostatics problem, and there's two more problems after that. One is similar to what we've already done. So we probably don't need to do it, and we can in fact probably do it, you know, if you want, we could do it in my office hours if you want to come by, or maybe we could do it in lecture or something. But or I could leave that one problem, you could do it, and then you're going to get the solutions. Just don't look at the solutions and try and do that problem because it's so similar to everything else we've done. What I'd like to do is do this hydrostatics problem and then go back and do the one that was missing the picture so that you see the picture, and we'll work that whole problem out. And if there's time after that, we'll do that last one. But the last one is very similar to what we've already done, so I don't want to take any more time doing another problem that's similar to what we've already done. It involves constructing a control volume around some known velocity field and computing the mass flux term. Steady flow, so there's no unsteady term. All right, this problem did not win me any friends, as I recall. So we should do it. I don't know what was going on that day, but I think this was probably too hard, this problem. But it's a hydrostatics problem, which we haven't spent a lot of time talking about. So let's do that example. All right, is there anything down here? Is that one clean? That's clean. All right, we've got this the strange channel. So this is spring 2013. And it's number 3. Okay? So we've got this. You guys did get the drawing for this? This is like a pig trough or something, like a trough that pigs would eat from or drink from or something. And it looks sort of like this. It's a half cylinder. And gravity acts peculiarly. Well, I guess that's peculiar. If the pig's trough is this way, gravity's in that direction, right? But we're going to put some coordinates on here. We're going to say this thing is filled with a fluid, so this is the free surface. Hydrostatic fluid. And we're going to put some coordinates on here so that this is the y direction. which is a little bit disturbing because we like to see G in the Z direction, but it's a cylindrical coordinate system, so we really need to align Z along the cylindrical direction. And so I'm going to put Z in the Z along the Z axis of this half cylinder. Okay, so this is X, and I guess I'll draw Z out like this. This is Z. I'm going to erase this thing here. Okay, so this is X, Y, and Z. But we're actually going to do this thing in radial coordinates. So here's R. So R points to fluid particles in this little lower half cylinder, right? So here's your X and Y coordinate system. G, and I'm going to move G. It's crowding my nice picture. So let's move G over here. G is ubiquitous, so we can put it anywhere we want. There it is. So G is doing this. Okay? And this thing has a radius, capital R. Okay? Of this half cylinder. Now, consider the channel in the shape of a half cylinder having radius big R that is filled with a static fluid. The free surface of the cylinder is exposed to atmospheric pressure. Okay, so we have P atmosphere out here. Acts all around this thing. Okay? Note, for the coordinate system drawn in the figure below, G is equal to minus G in the E hat Y direction, which I just wanted to make sure you guys didn't confuse that because I want the Z direction to move along the axis of the cylinder. X is equal to R cosine theta, Y is equal to minus R sine theta. Okay? And why isn't X equal to little r? It should be little r, right? Oh, I see, because we're going to integrate on the surface of the cylinder. So on the cylinder. So on the cylinder surface, and this is just a little aside, that's just your typical coordinate transformation you're used to from Cartesian to polar coordinates, right? Okay. And I also told you how the base vectors were related. So E hat R, because I didn't want you guys spending time on the exam trying to figure this out. E hat R equals cosine theta E hat X plus, or is it minus sine theta E hat Y. So these are little coordinate relationships between Cartesian and polar coordinates. Using direct surface integration, determine the net resultant force due to pressure, F. This is the resultant force due to pressure exerted by the fluid on the cylindrical surface of length L. Okay? So basically you want to find out what is the resultant force that the fluid exerts on this little trough, this drinking trough. Okay? And it's of length L. So let's say this is some distance back here. L to here. So that's L. So that's the whole length of the trough. Okay? So we want to find out the total force, the total net resultant force of that pressure acting on the entire inner surface of that cylindrical surface, exerted by the fluid on the cylindrical surface, assuming the fluid is incompressible with density rho. Okay, so we have some density in here, rho. And the channel is, here's the lovely part. And the channel is accelerated because, pigs, when pigs drink out of a trough, they're accelerating at some uniform velocity, naturally. It's accelerated uniformly in the positive x direction. Oh my God, why did I do, this part I didn't need to add. You see, this is just getting a little carried away. Didn't need to accelerate the thing. I mean, it just turns my stomach to even think about the pigs drinking out of the trough and uniformly accelerating. Is accelerated uniformly in the positive x direction with acceleration a equal ax e hat x, and ax is the positive constant. Compare result with the force due to the weight of the cylindrical channel for the special case when the acceleration equals 0. So if you stop the acceleration, the only force you're feeling is the weight. But I'm also going to accelerate these poor pigs in the x direction. So there's going to be an a equal to ax e hat x. And so obviously this whole fluid is going to tip, right? Some mad pigs, man. Assume that the channel walls are high enough so that the fluid does not spill out of the container. And you may find the following integrals useful. All right. I'm sure when the students saw those three integrals, they said, I want to leave. I hope I don't find those three integrals useful. I never, ever want to find those three integrals useful. Not even one of them. Useless integrals. All right, let's just do it, shall we? I mean, I don't know what I was thinking when I wrote this problem, but this was not humane. At least get rid of the acceleration. What's that?
Someone upset you.
I had a bad day. I don't know. I have no idea what happened. I'm not sure they even survived. That year there was nobody graduating. It was just these empty chairs. They all just found another thing to do. They all became artists. There's this giant artist colony. I don't know, guys. I don't know what was going on here. I didn't want to do this problem right now, but let's just do it. All right, so here we go. G is equal to minus g e hat y. Acceleration A is equal to ax e hat x. ER. That's the little base vector in the e hat r direction. I didn't want people to screw up the signs, so I just gave it to them because they'd all probably say cosine theta e hat x plus sine theta e hat y, or they might not even said that much. So I just didn't want to have any doubt about it. All right, the force due to pressure, which we defined very early in the semester, is equal to the integral of the pressure P over the area over which that pressure acts, n hat dA, where n hat is this normal vector here. Can anyone tell me what n hat is? What is n hat? It's this little vector that's pointing out in this direction here. So what would it be? Exactly. It's e hat r. Okay. Okay. All right. So n hat is e hat r. So this thing is just equal to the integral integrated over the surface of that cylinder, right? That's what that area is, of P e hat dA. And that further equals, and I've told you what e hat r is, It's the integral over the surface area of the pressure P times E hat R, which is cosine theta, E hat X, plus, or rather minus, sine theta, E hat Y, times dA. Okay. We still haven't used the hydrostatic equation yet. All right, now let's do that. So you see what this is? So I've asked you for the x and y components of the pressure force, okay, the force due to pressure. So we know that n hat is pointed, it swoops around, it's pointed in the E hat R direction, but E hat R can be expressed in terms of theta and the E hat X and E hat Y base vectors this way. So we'll substitute E hat R with this. Now from the hydrostatic equation, grad P is equal to rho G minus A. And that's equal to rho, what's G? Minus G E hat Y minus A, which is plus AX E hat X. Did I do that right? Yeah, it looks good. So in Cartesian coordinates, do you guys remember what's that? Everything good? Yeah. So in Cartesian coordinates, do you remember what this looks like? It's been a while since we did this, but how do you write the gradient of a scalar function in Cartesian coordinates? Yep. So the hydrostatic equation tells us that partial P with X, E hat X, plus partial P with Y, E hat Y, plus partial P with Z, E hat Z, must equal rho G minus A. So that must equal minus rho times G E hat Y plus AX E hat X. And we want to take the dot product of this equation, if you may recall, with respect to E hat I, where I progressively sequences between X, Y, and Z, to get the three components, the three scalar equations. So take the dot product of this thing with E hat I, where I equals X, Y, and Z in succession. Okay, so let's come over here and do that. So we have three scalar equations that come from this. Taking three successive dot products yields the three scalar equations. So the resulting three scalar equations are, what's the first one? I equal X. If I equal x, so we're taking dot product with e hat x, we're projecting that whole equation in the x direction. What do we get? What scalar equation pops out? Yeah? Exactly. What's the next one? And what's the last one? Yep. Everybody see this? Is all clear? Are we done here? So what is this equation? The easiest equation is the one that's homogeneous. What does this one say? Remember this from like a month ago or something, or 6 weeks ago, or 100 years ago? Neolithic times. Guy hit another guy with a bone, and they remembered that this was equal. What does it say about pressure? What is this equation here? This is the homogeneous equation. This is the one that has non-homogeneous, inhomogeneous. What's this one say? P is not dependent on z. Another way to say that is to say P is a function only of x and y. Exactly. Okay, that's good. So we've integrated up one equation. That was easy. So now we want to integrate these other two equations with this in mind. So integrating the first two equations and noting from the third that P is a function only of x and y, we get P of x and y integrating the first I think I'll give myself a little bit more room than that. All right, so if you want to integrate this thing, what do we get? What's that? Yes. Maybe or definitely. I would prefer, yeah, that would be good. Yes. Beautiful. Plus a function of y, right? Can't be a function of y and z because we know that this thing from this third equation, pressure does not depend upon z, right? So that's good. Now, let's differentiate this thing with respect to what? We're going to use the last equation. We've used the first equation, we've used the third equation. Yeah. So the only one's left is this equation, and so this equation is a partial derivative with respect to y. So let's differentiate. Although, if we were to integrate this equation up, we'd get some function. We'd get P is equal to minus rho g y plus some function g of x. So you'd have a function f of x, f of y, and g of x. You'd get there. You could sort it all out. It's a mess. It's not a mess, but it's a little cleaner, I think, to do this. Once you get this equation, you don't introduce a new function of integration. You introduce a derivative of this one. So differentiating this with respect to y and using the second equation, we get partial p with y is equal to, what's the derivative of this thing with y? 0. What about this? Yep, df dy or f prime. And what's f prime got to equal? The right-hand side of this equation, minus rho g. We did this exact kind of integration in class. Here, this one's for real. All right, can we integrate that? Integrating with respect to y. What does this integrate to? Yes. So f of y equals minus rho g y. What else? Plus c. Thank you. You guys have this completely figured out now. clearly f is a function only of y. The function of integration is a constant. You never did this kind of stuff, have you before? He's integrating up PDEs.
Multivariable.
You did do this? Integrating up like 3 PDEs? What?
Yeah, I feel like we've done it.
Okay.
I've definitely done it.
Very few students admit to having done anything before. You guys are very brave. Yeah, we've done all this before. This is cakewalk. Okay. So now we can combine all this mess and get what? Okay, so now we have the pressure as a function of x and y is equal to minus rho ax minus rho a sub x times x plus f of y, which is minus rho gy plus c. Or, if you like, minus rho times ax times x plus gy plus some constant of integration. Good. Now, at x equal y equals 0, right? So where's my little drawing up there? I spent so much time working on this guy. If you're right here, x equal y equals 0, what's the pressure there? C? C? Oh, come on. The pressure's never C. It might equal C, but it's not C. What's the pressure? Thank you, it's P atmosphere. What's the pressure? It's C. So at x equal y equals 0, comma, P equal atmospheric pressure, all right, which equals C, turns out. And we get P of x and y is equal to minus rho, is equal to P atmosphere minus rho times AX x plus GY. All right, so now we've got the pressure. This is how it varies. Good. Now remember, if AX were 0, right, it wasn't accelerating, then this would just be this would just be coming from we could determine the weight by integrating this thing. But if there were no acceleration, then it wouldn't depend upon x. And for all values of x, you'd be at atmospheric pressure when y is 0, right? So if acceleration were 0, then all values of x, where y is equal to 0, you'd have atmospheric pressure, as expected. And that's the free surface. But clearly, our free surface is tipped, and it's linear. It's a plane. It's an equation of a plane, and the xy plane gets tipped a little bit. And the bigger AX is, the more that plane tips. Right? The more that plane tips. And we can find out the slope of that plane relative to the horizontal by looking at this ratio of AX upon G. Good. Now, the gauge pressure, then, is just the pressure above and beyond atmospheric pressure. Right? And it depends upon x and y. And it's just equal to minus rho AX times x plus G times y. So this is the gauge pressure, which is what we're going to use in our next integration. Good. We're getting there. Now we have to go back and compute this thing. Right? So now we found the pressure. Okay? And we have to integrate this thing. Oh, that hurt. This guy goes down. No, he goes up. Okay, so using P gauge in F sub P provides
Would you have to specify the x and y, well, x to be positive or negative, but would you have to specify that y has to be less than 0?
it doesn't have to be less than 0 because the thing tips. So remember, when this thing is accelerating, pig's flying, right? Along with this thing tips up. In the back, for negative values of x, y is positive. Right? And for positive values of x, the free surface is at negative, begins at negative values of y, not at y equals 0.
The liquid is moving down the trough.
Yeah, what's that? Well, the whole trough is accelerating. It's really tall, right? So I've got walls I didn't draw up there, but there are walls that keep it from sloshing out. And so now you accelerate it in the x. You see how ax is accelerating in that direction? So the whole free surface, here's your cylinder, the whole free surface tips like this. And now when you're way back here, it's going to look something like this. This is what your free surface is going to look like. The whole thing's going to tip. So now back here, y is negative, it's positive. So all these points that behind x equal for negative values of x have positive values of y for the free surface. And then for all positive values of x, the free surface is at negative values of y as opposed to y equals 0. Does that make sense? Yes? Okay. Does that make sense to everybody? This free surface is tipping as you accelerate. Okay, so what's Fp equal to? Remember what Fp is equal to? It's equal to the integral over the area of the gauge pressure times cosine theta E hat x plus, or is it minus? It's minus sine theta dA. Because we're acting for the net resultant force. This is the net resultant force. It's Friday, isn't it? Yeah. So that's the net resultant force. So that means we're subtracting the atmospheric pressure outside of this trough from the entire force that the liquid in the trough is exerting on it. So we have to work with gauge pressure. Does that make sense? So you have atmospheric pressure up here pushing down on this, but we have atmospheric outside of this thing pushing back up. So the net resultant force is the gauge pressure, because you subtract the atmospheric off of the total pressure here. The total pressure in here is the absolute pressure, which is the gauge pressure plus atmospheric, and the total pressure out here is the atmospheric pressure. So we're subtracting off the atmospheric pressure to get the net resultant force. Okay? So that's why we can work with gauge. Good. Now, x equals on the cylinder surface x equals, remember, r cosine theta, y equals minus r sine theta. And F sub p, therefore, is equal to, what do we have here? It's this thing here. I've got to pop this equation into here. And we have a minus rho factors out of it. Rho times r times, well, let's do it this way. It's rho times, what do we have here? We have g ax cosine theta. Okay, we got to, I guess I have to do it this way. So we have PG, let's just put PG in there. PG is equal to minus rho times AX x plus, is it plus? Yeah, GY times cosine theta, wait a minute, yeah, that's right. Cosine theta E hat x minus sine theta E hat y. dA. Did I do that right? So it's minus rho times AX plus GY, that's the gauge pressure, which is here. Cosine theta E hat x minus, good. Now we can expand it out. And what does dA equal? Oh, we have to substitute x and y. So this is equal to minus rho integral over the area of a sub x what's x? On the cylinder surface, we're integrating on the surface of the cylinder. The pressure force is only down there, so we're evaluating down there. Capital R cosine theta, that's x, plus g, what's y? Minus R sine theta. And that whole thing is times cosine theta E hat x minus sine theta E hat y. dA. Now we're close. Oh boy. Can I delete this whole thing here? I'm going to get rid of this. And this is something you guys, this might be a little bit, you might be rusty on this part. We're going to find out evaluate the pressure at the center of this differential area element. PdA is little df, right? And the total force, pressure force, is the integral over the entire surface area of the trough times the little df, right? So df is equal to n hat p dA, where that's the differential area element. So you're finding the value of the pressure in the center of that little differential area element. You're weighting that dA by your local pressure. And then you're summing all these dF elements. So we have this integral over the area of dF is equal to the integral over the area of n hat p dA. Okay, and that's what this is. Right? That's your pressure force. So basically we're taking all these little differential area elements and and then wherever you see x and y, it's got to be evaluated on that surface. So x has to be capital R cosine theta on the cylinder surface, and y has to be minus capital R sine theta on the cylinder surface. Similarly, we need to find out what the differential area element is. Can someone help me with that? What is the differential area element? Remember, it's arc length times some other linear dimension. No, that's volume. That's units of volume. What was that? Is it getting too late? No dy. So I like this. That's the only thing I like up there. What's that? I only like the DZ. I actually never have liked anything but DZ in my whole life. Who said that? Very good. Say it again. What R?
That R.
This little guy?
That R.
I hate this R. Let's try this. Now that we've totally guessed at this, can we figure out why it's what I just wrote? See why I hated that thing? Okay, why is dA this thing? Think about the arc length. This is your arc length. I'm going to take that thing and draw it bigger over here. So this is your little arc length. This is ds, right? That's this little arc length. From the center here to the center point there is capital R. A little differential swing around there to sweep through this little arc length ds is capital R d theta. You see theta is coming down like this. This is theta. Does that make sense? You're on the surface of that cylinder. So big R d theta is ds, and then going in and out of the board, this is dz. So the total area is dz times r d theta. Isn't that nice? Okay, so where am I working? I don't even know where my workspace is anymore. Where did we leave off? This guy here? Okay, so dA is big R, something like that. Big R d theta dz. So this guy is big R d theta dz. Now, we go over here and we say, what is the left-hand side of this thing? The pressure force, right? It's got x and y components. And this is equal to, you'll notice there's a capital R common to both terms. Let's get it out of there. There's a minus sign here. I like that minus sign. Let's see where it is. Okay, so let's get it out of there. So FP is equal to, here we go, rho R minus rho R times the integral over the area of AX times cosine theta minus G sine theta times cosine theta in the E hat x direction minus sine theta in the E hat y direction. Right? And now we have this dA, which is capital R d theta dz. And can we now fix this and put a decent set of limits on this guy? Let's make it r squared. But I don't want to do that now just because I want to make sure you guys see that, and then I'll do it next time. You got to have a certain number of things to do each step, otherwise it gets boring. So what are my limits? All right, I like that. So z is going to be 0 to L. And what about the other one? What is that? I love all these pens going up, and it's like you guys, a bunch of conductors. What's that? 0 to what? No? I don't want to pull out a negative. Why would I do that? What's that? Oh, you want to integrate from pi to 2 pi. Okay. We can, all right, I'll integrate from pi to 2 pi if you like. I didn't actually define it. It's the same answer, guys. If I do 0 to pi, it's going to give the same answer. Or, yeah, that's why you wanted the negative, right? Okay, let's just do pi to 2 pi, and then we're all happy. If we want to define theta as being positive the way our convention, go pi to 2 pi. All right. Now do you see why I gave you all those weird integrals at the beginning? Okay, let's pull out the r, because somebody wanted to do that. And we are going to integrate, there's no z dependence anywhere in this problem, right? So we may as well say this is minus rho r squared L, right? Because we can integrate this whole thing with respect to z, and we just get a 0 to L, times the integral from pi to 2 pi of this mess. There it is. There's an x component and there's a y component. Yeah. Yeah, minus rho r squared. Okay. Oh, I made a mistake and I got 5 points off. Screwed up. Totally screwed up. That is the correct integration if the acceleration is 0. Oh, no, guys, I defined theta and I didn't show it to you. Yes, I did. I define theta as going downward this way. Theta is going downward this way. But that's not the mistake I made. That's not the mistake I made. I made another mistake. This is the right answer if ax were 0. Right? Integrate from 0 to pi. But it's not 0 in general. It's some non-zero value. So why would my limits of integration over here change if ax is non-zero? It's tilting. We don't start integrating from 0 to pi. We integrate 0, right? We have to integrate from some angle 0. So now you got your trough like this, and you've got this tipped surface. And here's the original. So no, we're not going to do that. We're going to add a new variable, phi, of course, right? So it tipped down some amount, phi, right? This was really obnoxious of me to do this. And so now we've got some angle theta, which is like this. Here's r, and this is theta. So now we want to integrate from 0 plus phi to all the way around to pi plus phi. So this should be 0 plus phi to pi plus phi. Does everybody agree with that? What's that? Did you say that? What did you say?
I feel like I would instinctually want to do that, but I do it because I'm running out of time to think that it's like illustrating what I want to do without actually.
Right. I understand. It does. It does make sense. It makes sense. But here's the thing. What did you say? I have no idea. I probably gave you points if you didn't do it. Extra 3 points for not doing it. So it turns out, carry out this integration, and you can use our little identities, right, to come up with this phi down here and this phi down here. They'll show up all by themselves, and they'll cancel out. You'll get these little factors of phi showing up, which will cancel out. Okay, so you're going to get the same answer. Yep. Mm-hmm. It's not really distributing them. It is distributing them in a sense. I mean, you could say this times this plus this times this. That's your way of distributing them, right? But I would just say this times this is the x component of f, and this times this is the y component. Okay? All right. So when you carry out this integration, and I don't think we should do this. No, because if we don't do this, we'll have more time to do the other, not to go leave early, mind you, to do that other problem, right? Which we all want to do. We're so eager to do that last problem, right? You guys can hang in there, right? You guys are sitting down. I'm expending all the calories up here. I got to tell you, I need another pizza. All right. No, I was kidding. I don't need another pizza. That was a joke. Oh, there you go. You have a pizza. Right? There's 600 pieces. So I'm going to just show you quickly what you get. I'm just going to write this down. So FP, when you carry out this integration, and you use those 3 little vector identities, right? I mean, I should just, in the future, I would just stop it right here. To the extent that I didn't give you this problem, I would stop it here. Okay? This is where the madness should have stopped on this problem. But I carried it through to the bitter end. And so I won't do that to you guys. I promise. I've got much better things to do with my life. So what you get is you get rho r squared L times this. You get an x component that looks as follows. Ax, I just want to show you how all this cancels out. 1/2 pi minus phi, plus phi minus phi, plus, this is from using those little vector identities, plus sine of pi plus phi, times cosine pi plus phi, minus sine phi cosine phi. That's e hat x. Minus e hat y times g times 1/2. And these cancel here. And this whole thing is a vector identity, which is 0. Sorry, I know. Hard to believe. That's 0. That's a vector identity. No. And why would you need them? How could a calculator possibly help? You're just vector identities? This is a vector identity. I mean, this is like a trigonometric identity. It does that? Does it do the laundry? What do calculators do now? Okay, there are no calculators coming into this room. All right? And by the way, all the cell phones, I have a picture on my phone. The first year I did this, all the cell phones come out, and they go up on the desk in front, and you put a sticky with your name on it. I mean, mute the thing. Please mute the thing. Otherwise, the whole table vibrates. Okay, and then I take a picture of all your phones because it's just so fun to have 40 cell phones out with little stickies on there. Yeah. No, I leave them all laying out flat. They're all well respected. So the AX has a minus sign in front. Well, I think what happened was when I did this integration, that sorted itself out. No, you're right. How did you know that? There's a minus E hat X there. Whoa, good job. Shouldn't there be a negative there? Whoa. You want to finish this? Okay. A half, and then we've got a pi plus phi minus phi again. And then we've got this other thing, which I'll write out, and then I'll make it go away. I'm pretty sure I gave you that, didn't I, in this problem? I gave you this vector identity. I mean, this trigonometric identity. No, I didn't. I didn't. I must have told somebody this. Anyway, that's gone. That term is 0, too. And then we close this with a curly brace. And what you find out is, note. I love these notes. Note that the cosine squared, what was that? Well, Raj will tell me later. The cosine squared of pi plus phi, though you may not remember this, minus cosine squared phi, guess what that is? Of course. And therefore, this whole thing is 0. No, it's not. It's not. It doesn't. Well, it does a little bit. Hold on, let's just see here. What you get, no, it doesn't do anything. It's totally fine. Thus, f sub p, it's just not an issue, equals minus pi upon 2 rho r squared L ax E hat x plus g E hat y. The whole thing reduces to that. So it doesn't matter that the water tips in the container, because where it increases the pressure on the back, it takes away from the pressure where it drops. So where it drops off, you've got atmospheric on both sides, and so that subtracts from the total F sub p. When it tips up, that is completely matched, mirrored over here by the stuff that's added over there. So, as far as I'm concerned, we should never do a problem like this again. But as far the top line is good. You're good right there, except for the mistake, because the integration technically has to be like that. And then all those trigonometric identities take you all the way home and show you all these things that cancel out. But the top line, as far as I'm concerned, that's all I want to see. I don't know why I made them go further. Why do that? Was that one of your tests? No. Here's the next. This is the last year I taught this class. Yes. I think they keyed my car that year. All right, so now we have time for one last problem, and then they shut the garage down. I think we did really well, don't you? I mean, we did everything, but we'll get this one last problem done, and then we will have done everything but with an 8 of the 9. And the last one is very similar to one we've already done. So now we're going to do this little microscopic one, okay? And I'm going to draw the picture. Whew, I've got nothing left to drink, so we got to go home soon. All right, here we go. Problem number 8. And this one is another Bernoulli. And it is hard to see, so the glasses have to go off. So this is fall 2001. How old were you guys? 6? You were 5? Wow. 1996, you were born? You're 95? You're old. They were 6, Raj. He says, slightly embarrassed. He was 10. Okay, not quite. No, what's that? You were 8. 6. Really? You're only 2 years older than some of these people? You were born in 92, I thought. But you should see how accomplished he is. He's 2 years out of college. What's that? I know. So you're 4 years older than the seniors here. Yeah. 93 and 96. Oh, you're 3 years older than you. Oh, you were born in 95? And you're 93? 2 years older than you. Okay. 94? Are you a senior? Oh, okay. 94, so you're a year older than this guy. Okay. So but Raj he skipped for secondary school. He just went right from cradle to college and did 2 majors and a minor. So don't talk to him. All right. So this is fall 2001. That does seem like a long time ago. Problem number 1. Wow. Okay. Let's draw this thing. I know it inspired me to do this. My parents still had a lake house, and I used to have to purge the. We used to have a well water pump. So we had a lake pump. So all the outside spigots were powered by lake water, or were supplied by lake water. So in the basement of the house, my parents' lake house, and this is in Connecticut, we had a big holding tank. And we had a pump, and I had to rebuild that pump. Had a little impeller-driven electric motor, a 1-horsepower motor. And I needed to rebuild the impeller, so I rebuilt the impeller because it was dying, put a new motor on there. And then, I got to learn how the whole plumbing system works. But basically, the pump sucks water out of the lake. Never mind, this is not this problem. It's a different problem. But no, it is this problem, right? It sucks water out of the lake, and then it sends all the water out to the spigots, right? But how do you pressurize that system? You pressurize that system with a bit of compressed air at the top. So you have this big, tall cylinder, big tank, full of water, but not completely full of water. You've got a little pocket of air at the top. And what you do is you turn the lake water pump on. The lake water pump is pumping water in, and then it primes all the spigots, but the spigots are closed, so it's a closed system. So now you get this incompressible fluid, i.e. lake water, being pumped into this tank. And as it fills up, it starts compressing the air pocket at the top of the top of this tank here. And the more you compress the air, the greater the pressure your system is. So the lake water holding tank is in the basement, and the spigots are upstairs. They're at ground level. So we're pumping water up again. We're not using a water tower and a hydrostatic head. We're pressurizing the whole system with an impeller-driven pump, and we're compressing this air at the top of this little tank. And that little pressurized air pushing down on this fluid. There's no hydrostatics. In fact, it's working the other way around. That pressurizes all the spigots. So when you open the spigot, it just sort of pours out. And that pressure up top starts to decrease as that water drains out. So open upstairs, you spray in a hose, right? As you do, the water level recedes, and as it recedes, the pressure in the air pocket up top decreases. And you've got a little pressure sensor in the air up there, and once that pressure sensor drops below a certain level, like a thermostat, it causes a lake water pump to kick. It starts pumping water in from the lake and starting to raise that thing up. So as long as the impeller can pull water in from the lake faster than the spigot can let it go, you can maintain equilibrium and have that constant pressure in there. And it's controlled by a regulator just like a thermostat, right? And of course, occasionally I would put too much water in and the water would go up above the little pressure sensor and you get filled with water. Pressure sensor doesn't work if it's filled with an incompressible fluid, it's got to be filled with air. So I learned that lesson the hard way. So you have to drain the whole system. Anyway, these are things I did in the 80s. So this made me think about this problem, right? So what we have is we've got this holding tank in my parents' house, right, in the basement. And there is a free surface here, and there's row of air. So the pressure of air up top, which depends on time, right? Because so this is exactly the lake water problem. So this thing, the pressure up there depends on time. It's not atmospheric, it's above atmospheric pressure. And it's escaping out here at your spigot at atmospheric pressure. So we have P atmosphere, we have a velocity 2 coming out of your spigot upstairs. And we have an atmospheric pressure up here too, outside. And there's a diameter of this little spigot outside called D2. The velocity coming out is V2. And we have gravity. Nevertheless, we have gravity here. I'm going to call this Z. And there's some height, h of t. We have a density here of water. So you have density of water here and density of air up there. Now, G is doing this. All right, let's read this little dissertation. Consider the cylindrical holding tank of diameter D. Somewhere is diameter D. Diameter D. This is a closed holding tank of diameter D and height L. Where's L? There's an H. L is this thing. Who cares about L? Do we need to know about L? And I'm going to call this whole thing L. Maybe we need to. I know. We do need to know L. I remember why. It's only 16 years ago, so it's not that hard to remember. Okay. There's L. Wow, this problem was, I did this one right after 9/11. I can't believe it's that long ago. All right, so this thing is of height L, shown in the figure below, which is initially closed and contains a liquid of height h naught. So at time t equals 0, h of t equals h naught. So h at t equals 0 equals h naught, right? And then it says, at time t0, a valve is opened and the tank begins to drain from a pipe of diameter little d, at the bottom of the tank. At t equal t infinity, when the tank is completely drained of all the liquid, the air is at standard temperature and pressure. Okay, it's okay. So when you drain all this stuff out of the water, there's no lake pump. Lake pump is broken. Okay, so this thing just drains out. At time equal t sub f, when the tank is completely drained of all the liquid, the air is at standard temperature and pressure, P, and I'm using the ideal gas law. So at T equal TF, PF of the air, the pressure of the air remaining in the tank, is at standard temperature and pressure and is determined by the ideal gas law to be rho of air, it's the final density, times RT, where T is the ambient temperature. Note, while the tank is draining, the mass of the air is constant and given by the mass of the air never changes. Right? There's a fixed amount of air in there. It's just the density of the air is changing. The mass is the same, but the volume of air is increasing. Mass isn't changing, so the density is going down as the tank drains. Does that make sense? Air density is going down as the volume increases, but the total mass of the air can't change. It can't come or go. It's stuck behind this liquid water underneath it. It can't percolate out. It's in a cooling tank. And so this mass of air stays the same, and the volume just increases as the density of that air goes down. So this is highly pressurized compressed air up here. The mass doesn't change. Okay? So the mass of the air is equal to the density of the air at any time t, at any instant t, times the volume of the air at any time t. Right? So rho v is mass equal rho v. It's mass over density equal mass over volume, right? So that's the mass of the air, which is always constant. I wasn't going to share that piece of information with the students, and I just felt sorry for them, so I just said, know this, right? The mass remains constant, even though the density is decreasing because the volume is increasing. Product of the two remains constant. Obtain a differential equation governing the instantaneous height h of t. So determine the ODE governing h of t of the liquid in the tank that depends only upon rho g in atmospheric pressure and the geometric parameters appearing in the figure. Assume 1, the liquid is incompressible. Having constant density rho. Obviously the gas is not, but it satisfies the ideal gas law. Okay. And 2, the air behaves as an ideal gas. Oh, and there's another thing. So we're going to assume 1, 2, and 3. The flow is isothermal, adiabatic, and frictionless. Okay. Neglect spatial variations in the density of the air, which we always do. We never consider the hydrostatic pressure head due to the air, right? We always neglect that. And the effects of acceleration associated with the liquid. So we're basically saying the liquid drains so fast that you can neglect the effects of acceleration with the interface, right? Okay, so let's do this problem and then go home. So let's start with the conservation of mass. So rho equal constant, time varying control volume. So what we have here is I'm going to draw my control volume up here. There's your control volume. So you have an n hat here. And do I call that 1? Yeah. N hat 1. And this is n hat 2. And again, if we have a time-varying control volume, remember we did a problem like this, where we said let's allow the control volume to shrink with time. Okay? So at 1, there's no flux of mass across the control surface at 1 because it's receding exactly as the control volume is shrinking away. So there's no flux of fluid across that surface, right? So we're going to do that time-varying control volume again. So, where are we? Oh, I think I'm down here, right? Yes. Okay, conservation of mass. So we have at V1, taking, assuming using, not assuming, it's using a time-varying, remember we've got I want to derive an ordinary differential equation for h of t, so it's natural to use this time-varying control volume because we're going to get a dh dt out of that. So using a time-varying control volume drawn above, we have V1 equals 0, n hat 1 is equal to E hat z, right? Z is upward. And therefore, V1 dot n hat 1 equals 0. V2 equals V2 E hat x, I guess, and n hat 2 equals E hat x, such that V2 dotted with n hat 2 equals scalar V2. And we have partial with t, integral over the control volume of rho dv, plus integral over the control surface of rho v dot n hat dA equals 0. Okay? Now, rho is constant. This is for the fluid. For the liquid. So this whole thing is for the liquid. I just want to remind you. We're looking at the liquid inside, not the air above. The liquid inside the holding tank. So, rho equal constant, which is not equal to 0, comes out of the control volume. So you get rho times partial with t, integral over the control volume of dv, plus integral over the control surface of v dot n hat dA. And this whole thing equals 0, but rho can't vanish. So this gives us this gives us dv dt plus the integral over a2, because there's no flow across 1, right? Because the surface of that control volume is receding just at the same rate that the fluid at that interface is falling down with it. So there's no flux of fluid across that interface. It always remains an air-water interface. Air on one side, the top, and water on the bottom. So there's no flux of fluid across that control surface because it's dropping as that control volume shrinks, as h of t shrinks. I could make, it's all going to be 0. So you could have an n over here, like an n hat 3. You could have an n hat 4 if you want to. But all the velocities are 0. You can even have another one over here. But it's a cylindrical tank, so n hat 3 could be E hat R if you like, something like that. Yeah?
So on the exam, can we say that we get this on the exam, can we do without the N4 and the N?
Yes, I think so. Just show us where you've got fluid paths going through it. Okay? And in the special case of the top one, you should make it clear in some words that because if we do a time-varying control volume, there's no flux of mass across that interface. So V is 0 at the interface. Okay, so dv dt plus the integral over a2 of v2 dA equals 0. But v2 is constant over the cross-section, right? So now we have dv dt plus v2 a2 equals 0. And what is dv dt? What is the volume V? Exactly. Everybody see that? The volume of liquid in that tank at any instant has to do with the instantaneous height times the cross-sectional area, which is pi d4 over d squared over 4. So this becomes pi d squared upon 4 dh dt plus, what's the area going out? It's a little d squared. Why is it d sub 2? Isn't it just d? It's not d sub 2, it's just d. Little d. Plus pi little d squared upon 4 v2 equals 0. And we lose pi over 4, and we get dh dt is equal to minus little d squared over big D squared times v2. What? Oh, I see, yeah. Yeah, right. A little d squared over big D squared times v2. Okay, good. So now we have dh dt, and v2 is equal to minus dh dt times, yeah, good. All right, so there you go. That's an important result. But we're not done, right? Because now what we need to do is apply the ideal gas law, okay? Because what's happening here is we ultimately want to get a solution for h of t as a function of rho, g, and p atmosphere. So pressure's got to enter into this, and Bernoulli equation is going to do that for us, okay? But we do need to do a little bit of work with the ideal gas law. So we need to, in order to let's start with the Bernoulli equation. Let's write the Bernoulli equation down, and then we're going to have to take a little detour to find out what P1 is, which is the pressure at 1. So now let's apply the Bernoulli equation. So let's leave those alone and apply the Bernoulli equation. Because we have to introduce the pressure, because I'm asking you to write this solution in terms of P atmosphere. And so you know this is I've told you to assume an inviscid, steady, approximately steady, right? Because it's a very slowly draining tank. So I've said to assume an instant, approximately steady flow, right? What's that?
I feel so gross right now.
Oh, you do?
Doing the same tear for...
It is gross. I know. I've got the better deal. I'm pretty sure of that. Okay, so let's look at the Bernoulli equation, and then we'll have to circle back to the ideal gas law again in a moment. So now what we're going to do is we're going to take the liquid is incompressible, isothermal, adiabatic, and frictionless. And since we shall neglect effects of acceleration associated with the liquid at the interface, the steady state Bernoulli equation applies. And we're basically going to take a streamline, if you will, that goes from the surface up here, and imagine a streamline of the flow that goes out like that. So this is, any one of these things could be a streamline that do this, right? This could be another streamline. But they all start at the same pressure up here, P1, right, all these little streamlines, and they all leave at the same pressure, P atmosphere, down there. But the pressure P1 is changing with time. So we're basically applying the Bernoulli equation instantaneously and acknowledging the fact that the things are evolving at a very slow pace. It takes a long time to drain this tank out. So at any instant, it's pretty reasonable to neglect acceleration because it's so small and apply the Bernoulli equation, which is what we've asked you to do. So looking at any one of those streamlines, we have P1 of T plus rho, the kinetic energy term, rho on 2, V1 of T squared, right, plus rho G Z1 of T is equal to P atmosphere at the outlet, which is 2, right? And plus rho over 2 v2 squared. And finally, which is also a function of time, very slowly varying function of time, plus rho gz2. All right, now let's simplify this a little bit. So 1 and 2 are points on the same streamline, right? And we know that P1, let's see. So let's look on the left-hand side. V1, what is V1 of t? What's the velocity of the interface? It's very, very slow, but it's drifting downward. What's that? Minus dH/dt, right? dH/dt is negative, right? So the velocity is in the, let's see here. Does that make sense? It's in the minus z direction. Yeah, but the velocity is in the positive. Yeah, right. So we want dH/dt is a negative quantity. But if the streamline, if we're on the streamline here, and let's say this is the s coordinate on the streamline, and we're moving along the streamline like this. This is the way the path of the fluid. You want to look at the path of the fluid particle. It moves down the streamline like this and out, right? So it's going to have, the velocity here is going to be in the positive s direction as it is over here. It's not like you're going to have a negative flow up here and a positive flow up here. The velocity up here is in the same direction along the streamline as the velocity down here. So you've got to think about the velocity in terms of on the streamline when you're doing the Bernoulli equation. When you apply the Bernoulli equation, you say, what's the direction of velocity in the s direction, the plus s direction? So here v is in the plus direction, but dH/dt is inherently a negative quantity. Does that make sense? So if dH/dt is a negative quantity, v is in the positive direction. It's got to be minus dH/dt. Okay, so v1 is minus dH/dt. And what is z1? Thank you. Good. And what's next here? What's P2? Oh, I guess I should have called it P2. I shouldn't have let the cat out of the bag, but it's pretty obvious, right? P2 is always constant and equal to atmospheric pressure. V2, we have an equation for that. It's over there. So we can, put this back up. We can solve for V2 in terms of dH/dt. So V2 is equal to minus big D squared over little d squared dH/dt. Right? So V2 is equal to, and this is from the conservation of mass, V2 is equal to minus dH/dt times big D squared over little d squared. This is from the conservation of mass. And finally, z2 of t is what's that? Or it's not even a function of t. It's 0. All right, this is kind of a bookkeeping, but we don't know yet what P1 is. We're going to have to come back to that in just a minute. The pressure at 1 has to do with the pressure of that ideal gas and how that's changing with time, which we'll get to in a minute. So now let's populate this thing. So we have P1 of t plus, by the way, notice that V2 is in the positive s direction. What's going on? Am I going to get locked out? Okay, let's finish this up quickly. So, wow, I can't believe, I thought it was like 10:30. Damn. All right, so notice that this is positive, right? D over D squared is positive. dH/dt is negative, and that's a minus sign here. V2 is in the plus s direction. That gives you a good sanity check that this should be minus dH/dt, right? That makes sense. You've got this big giant thing slowly moving down at a minus dH/dt, V1 is, and V2 is the same thing, but it's accelerated. You know, you throttle the flow because you've necked it down to a tiny little hole, tiny little d, and so the difference in velocity between V1 and V2, the conservation of mass, is just the ratio of the diameters, just as we've all come to realize. All right, so P1 of t plus this guy, so it's going to be minus rho over 2 times V1 squared, which is just, this should be plus dH/dt squared, plus rho g, and what's Z1? It's h of t, is equal to P2, which is atmosphere, plus rho on 2 V2 squared, which is this thing, dH dt, quantity squared, times d to the fourth over little d to the fourth, plus rho gz is 0. So this is it. But all that's left is to get this guy. How does the pressure, and then solve this mess? How does we're not going to solve it because it's a differential equation. So to finish this up, how do we get P1? We need to know how the pressure varies. How the pressure varies at the interface. And that has to do with how that, from the ideal gas law, how the pressure varies in the gas. Where would you put it? And it should be free, right? Yeah. You know where it's parked? Second floor? He's incredibly handy. This guy's unbelievable. Should have just had him build the Subaru. Thanks, Raj. Okay, so from the ideal gas law, you need to reset that thing? Yeah. Have to go home after this? Problem 9, we're all exhausted, right? I'm looking at people here. You guys are changing phase. You're just turning into a liquid. Okay, so from the ideal gas law, we're going to neglect spatial variations, right? We said that. We always do that with gases. In the air density, so P1 of T equals the pressure of the air, right? So the whole pressure of the air tank is constant. And way at the beginning of this thing, we have something about the pressure of the air, which is rho f of the air times RT, if you may recall from the beginning. So, and the pressure of the air in the upper portion of the tank is given by P of the air of T is equal to rho of the air times RT from the ideal gas law, remember? And that is equal to the mass. So now we may recall from this thing way back before, mass of the air is equal to density of the air times the volume of the air, and that's constant. So that's equal to the mass of the air upon V of the air, right? Because rho of the air is of T times RT. Does everybody see that? So if you look at the mass, which is a constant, the mass is equal to rho times V, which means that rho is equal to the mass of the air over the volume of the air. That's all I've done. Okay? But this is a constant. This never changes in the whole problem. However, the mass of the air is constant, and we know what it is at the very end of this experiment, when all the water is drained out. So it's constant and given by m of the air is equal to, like we have over there, rho of the air of T times V of the air of T. And that's equal to okay, so what's the volume of the air? So the volume of the air, what is this thing equal to? So this is rho of the air of T times the volume of the air of T. And it's kind of like the way we found the volume for the liquid in the tank. Same cross-sectional area, pi d squared over 4. And what's the length, the height of that air column? What is it? L minus h of t, right? It's not just L. What's that? No, I didn't say that. The mass of the air is constant and given by this, right? As a function of time. When it's empty, h of t goes to 0, and the mass of the air The volume of the air goes to pi d to the squared over 4 times L. But at any instant in time, it's L minus h of t. Okay, so this is equal to, since this is constant, this is equal to the final value, as I have up above, rho subfinal, v subfinal, and now we get back to Ross's answer. He wasn't silly, he was just ahead of the game. So this is equal to rho air final times pi d squared over 4 times L. Right? So at the very end of the day, all the liquid leaks out, drains out, and now that's the total volume. Right? So, therefore, all right, do I need to, oh no, what am I going to do here? I guess I can move, I'm done with this board. So it's just this guy. We've got to finish on this board. We're running out of chalk. Okay, so finally, therefore, P of the air as a function of t, let's go back to this board here. Let's go back to what P of the air is. That's this thing here. P of the air, remember this guy, is equal to rho of the air times r of t, which is equal to mass of the air, which is constant, all over v of t of the air times RT. And that equals the mass of the air. Now we're going to substitute in the mass of the air, which is rho air sub F. And we know what that is. Right? That's the standard temperature and pressure times RT. All right, let's see if I understand this. Rho of the air T is equal to rho F. This is 16 years ago. So this is rho F of the air times RT. That's fine. It's the mass of the air. RT. Right, so it's this thing and that. Times the volume, so it's 1 over the volume, so I have to invert that thing. So I've got to invert this guy. So now we've got pi d to the 4th over L, pi d squared over L, pi d squared over 4 times L, all over pi d squared over 4 times L minus h. Okay, let's see if we understand what's going on here. So this is rho of the air. Here's our RT. And here's rho air final, which is this thing here. Rho air final times pi d squared L. Right, that's the mass of the air. Rho air final pi d squared L. Rho air final pi d squared L times RT. All divided by the volume of the air, which is down here. The volume of the air is pi d squared over 4 L minus h. Okay, that's the volume of the air. Does that make sense? So this volume of the air, this thing here, equals pi d squared over 4 L minus h. And this thing here, m of the air, is equal to rho F air pi d squared over 4 L. Does everybody see that, where that comes from? Good, but there's one last thing to notice. What is this equal to? Yeah, it's P atmosphere, right? At the end of the day, all the stuff leaks out. What's the density? What's the pressure in the gas? It's P atmosphere. Okay, so this whole thing is P of the air final, which equals P atmosphere. So this whole thing equals P atmosphere times pi. The pi d squared over 4 cancels, doesn't it, here and here? So it just becomes L upon L minus h of t. And now that, finally, this thing here gets substituted into the Bernoulli equation, and you get P of t, P air of t, shows up somewhere, right here. Where's the Bernoulli equation? Up here? This thing is equal to P air of t, which equals P atmosphere times L over L minus h of t. And the final equation looks like this. We get P atmosphere L upon L minus h of t is P1 plus rho over 2 dHdt squared plus rho gh of t equals P atmosphere plus rho upon 2 times dHdt d to the fourth over little d to the fourth. And that's it. That's the answer. But if you want, that's a differential equation for each. What's that? This should be squared, I think. Is that right? Yes. It's a nonlinear equation. So that's this is the equation, as far as I'm concerned, for governing h of t. You could, just rewrite, do some algebra on it, but it doesn't change it. Change the fact that that is the equation.
What a day.
Yes, and mine started early. I've been very busy today.